and it goes to the magnesium-rich side. And the only message here is look at the richness of the picture we obtain, which tells us that the magnesium-nickel system is not as simple as maybe many have believed, but there is a lot going on. Okay, now let me show you that what we can also do, which is to not look at the final picture, but it's also to monitor the system while we are loading it with hydrogen. So this is, again, a very mild situation. We talk about 15 millibar. This is a little bit higher in temperature than what I said before. At this temperature, these are the millibars, yeah, and this is the plateau pressure. What we obtain then is this. Maybe I should explain what this means. Look first at the composition. So here on this side, we are on the magnesium very rich side, and here, here we would have roughly magnesium to nickel. So this is a gradient sample, okay, magnesium rich here, and going about to magnesium nickel 1:1. The vertical axis is time. So you look always at the same sample as a function of time. So the sample, let's say, appearance is on this graph only one horizontal line. And you see that some concentration need more time to react with hydrogen than others. You also see that this is very bright, transparent, and here there is some modulation. Okay? Now, let me give you a detail of this picture, which is, you see the connection. Huh? In the green rectangle, it's exactly what is contained here. And I just want to show you that we can, at a given time, we can make a cross-section over the optical transmission, and you obtain something like that. Or you can decide to be at the fixed composition, and then you're on this vertical line, and it gives you the kinetic of the hydrogen absorption. Now, is this important? Yes. If you do the simplest model, I'm not going to describe it, but I think that this morning Andreas was already introducing the main ingredients. You come with an H2 molecule here, you have some surface processes taking place. You may have subsurface states, you may also have an oxide layer. Let's symbolize all this with this here, and you have a metal hydride. And you want to know what the pressure, the plateau pressure is of this metal hydride. And you don't want to do anything else than looking at the sample. Okay? So, hey, this does not work. Well, anyway, you were supposed to see a hydrogen moving from left to right, but it has landed here. Okay, so you believe that. Now, the thinking behind the idea is that even if you are surface barrier limited at the surface or diffusion limited, the rate of absorption depends on the difference of the gas pressure here and the equilibrium pressure, plateau pressure of the hydride you are looking at. So just remember, the rate should go to zero. Sometimes it goes like a square root to zero, but the important message is it goes to zero. And then you do measurements, and for example, at 90 degrees C, you see that if you are at a relatively high pressure, this is about 46 millibar, then you have a rate which is relatively high. If you are at a lower pressure, then you have a smaller rate. And you see that if you just accidentally choose the right pressure here, you have essentially no rate. This happens to be a straight line, it's fine, and I just want to draw your attention that we get a straight line at 90 degrees, 60 degrees, 20 degrees. You look at the pressures which are at the intersection, then you do what Andreas Strittel showed you and many other people. You do a Van 't Hoff plot. These are exactly the 3 points I showed you before, and from this here you can determine by using a famous equation, you can determine the enthalpy of formation. And you do that, and these are the results we obtain. And there are a few things I want to stress out. These here are 1001 optically derived heats of formation. This is a measurement which lasts about 1 day. It takes slightly more time to analyze the data, but this is what you measure. You measure all the systems at the same moment. maybe also important is to see the values. We are in kilojoule per mole H, okay? So we are around minus 30 here. And if you look at literature values for thin films, this is exactly what has been reported in the literature. What we also find as a function of concentration, you see this here would be magnesium, no, this is 1-to-1 roughly, and this will be magnesium rich, okay? We have three regimes, one where we have two plateaus, and this is new, I guess. No, it's not new. Many people have had two plateaus in magnesium nickel. But in thin films, we have a plateau here which is at minus 24, and we don't really understand why it happens, but it really happens. And this would make magnesium to nickel an interesting material. Out of this brown region, we have single plateaus, and you see that the heat of formation is still not very different from that of pure magnesium to nickel H4. Okay, now I want to show you that you can use the same technique for magnesium aluminum, and this is what we have measured. Look at the photograph. I don't know if the contrast is good enough for you, but the red, green, and blue channels of the CCD camera are shown here, and you really see that there is something happening, which is this wide band here, at a composition which could correspond to magnesium alanate. We don't know if it is really magnesium alanate. What we can certainly say is that our films, which are evaporated, we just sputter magnesium and aluminum metal. We cover a little bit with palladium, that these films have a clear enhanced reactivity with hydrogen at a composition which would correspond to the magnesium alanate. Okay, now let's go to something else. I mean, it's not very original to talk about magnesium transition metals, but it's just to illustrate the technique. Of course, making a gradient from magnesium to rich to nickel rich is educationally correct, but I mean, for combinatorial purposes, you would like to be more complicated. So I give you this here as an example of a ternary system, and it is magnesium, nickel, and cobalt. And the trick here is now you use three sputtering gun. In fact, we have 6, and we can do more complicated games. But let's say these 3 here. You sputter again magnesium, you sputter cobalt and nickel on now a wafer which is 3-inch in diameter. And what you obtain after loading with hydrogen is this picture. This is the picture I showed you before. Now, if it works, you see a little movie here, which seems to work. And this is as a function of time, what you see with the camera. And the message I think I would give here is we have sputtered magnesium from this side, nickel from this side, and cobalt from this side. And you see it is extremely rich. There are regions which differ by only very small fraction of concentration of cobalt and nickel, which have a completely different behavior as a function of hydrogen loading. Now, Philippe Moreau, who is working in our group, but who came from Fribourg, has designed an algorithm to translate the picture you have seen before, which is this picture here, into a ternary composition picture. So you have magnesium here, you have nickel, and you have cobalt, and the photograph you have seen before, translated now in a compositional picture, correspond to this here. You see this little needle here, which was this needle here, is only a tiny part of the, let's say, ternary phase diagram. And of course, you can also start the picture here. You can see as a function of time how this system reacts with hydrogen. And again, for us at least, we are physicists. We were used to work with clean systems. We did not expect so much action in a system like that. Okay, now I will show you that you can also look at very detailed of the system. At first sight, this looks the same story as just before, magnesium, cobalt, and nickel. But if you translate this here now in a phase diagram, the sample has been done in such a way that the cobalt source is only at most depositing 10% cobalt. So we are talking in the phase diagram of a very small region, a sort of band at very low cobalt concentrations. And here again you see that a lot is going on. So we are talking about concentrations which are, let's say, between 2% and 10%. Now, these are photographs. Everyone with a reasonable CCD camera can do the same thing. And we wanted to do more than that. And Martin Slauman designed a little fiber optic setup, which is shown here. So now you recognize maybe this is the chamber where we can put our 3-inch wafer. We have two fibers, one from the top, one from bottom, and one is used to do optical transmission, and the other one to do optical reflection. And we can scan through the sample, and we can measure what the optical properties are. And I'll give you the two things. Of course, the CCD camera gives you a much nicer picture because we have many, many pixels there. And this here is now the scanned picture. So you have to imagine that this fiber is scanning, and the side of view of this system is, let's say, about 5 by 5 millimeters. So that's why you see a sort of discrete steps here. But I hope that you see that this picture here resembles very much this picture. Now, the advantage of this scanning technique is that we can look very carefully at the optical properties at specific points, and I'll just took 3 here to show you the differences. Without going into the details, you just look at transmission, which is a red curve, and reflection, which is the blue curve, and I don't want to do any physics here, but everyone will see that, that these 3 spectra are totally different from each other. And we have learned in the course of time, we have learned to interpret this, to translate these spectra in hydrate properties. Okay. Now, well, I'm doing almost fine with my time. Another thing, which is also a game which is very useful, is, for example, to look at catalysts. And the simplest game you can do is to take a catalyst and put it on a switchable mirror. Let's say our gold, very old friend, yttrium. So we put just the catalyst, we sputter it on a switchable mirror, and then you just have to look at what happens. Oh, this little cartoon is not moving. You were supposed to see the hydrogen molecule going down here, then physicist option, chemist option, and then going down in the switchable mirror. The switchable mirror will tell you immediately how many hydrogen atoms have crossed the catalyst, and therefore you can optimize catalysts, you can optimize the thickness of them, and so on, in a rather efficient way. Now, I will stop here. My only purpose was to show you that with this optical technique, we have in principle the possibility to measure, if I just exaggerate a little bit, 10,000 samples in one afternoon, okay? And we hope that we will find the big treasure Ferdinand has promised us. So thank you very much for your attention.
Thank you very much, Ronald, for this very interesting and very visual talk. Questions? Yes.
It would seem in your very, very interesting presentation that you could also explore the effect of morphology, a degree of crystallinity, a degree of amorphous nature, degree of particle size, and the effect that these variables would have on the nature of the interaction with hydrogen. And of course these, I presume, would be greatly dependent on the rate of deposition, which would be controlled by the, in part at least, by the temperature of the substrate.
Yeah, that's completely correct. In fact, there are several parameters you can use to fine-tune the surface, to fine-tune the growth, and so on. We have, for people interested in optical and switchable mirrors, we had a physical letter last, November or something like that, where we have these switchable mirrors going from mirror-like to black. And in fact, this is really the influence of a defect structure. We discovered that it's a funny story. You take a glass and you evaporate magnesium to nickel and a little bit of palladium. And you put in the hydrogen, and what you see is that the hydrogen goes very rapidly along grain boundaries to the interface substrate magnesium nickel. And there it nucleates the magnesium to nickel H4 phase first. So while the hydrogen is coming from the top of the sample, it nucleates first near, let's say, the glass. And I heard a few times today that silicon was sometimes a catalyst. And we were looking in the possibility that we would have a catalytic effect. But it's also a fine structure, a defect structure. With TEM, we see that the grain size near the interface is clearly smaller than further away. And you can tune that by choosing deposition temperature, the substrate temperature, and so on.
Very, very interesting. Thank you.
Any more question? Yes?
Yeah. You mentioned you're using a palladium film, and I suspect that produces hydrogen atoms. So are you accessing phases that you might not make if you didn't have a palladium film there to produce hydrogen atoms?
I heard a lot of phonons, but there was a lot of can you repeat? Sorry.
I'm sorry. The palladium film on top of your samples will dissociate hydrogen molecules to hydrogen atoms.
Yes.
So are some of the phases you're seeing a function of that palladium? You may be accessing phases you might not access without the palladium to produce the
clearly.
atoms.
The message that we have here, let's say the arrogant message we have, is that when you put palladium on a film in a suitable way, you actually measure the intrinsic thermodynamic property of the material. I know it's a little bit arrogant, but the fact that at 100 millibar and room temperature we can make magnesium to nickel H4 tells you that palladium is helping very much. Okay? So, we don't have problems of first activating the surface and so on. But we're also looking looking at other catalysts, for example, stimulated by Thomas Claassen in Geesthacht. We looked at niobium oxide and other transition metal oxides on magnesium. And actually, we find that niobium 205 is a rather good catalyst for magnesium, but compared to palladium, it's miles away.
Yes, Keith.
Yes, can
Ronald, sorry.
You have two.
Yeah, okay, go ahead.
Okay, Joseph Toyota. It's quite interesting. And do you have any test measuring the coexistence of the moisture or repeatability of those?
Yeah. Okay. This is a very important point.
Yeah.
And in fact, it's not something we fully control. So, we can make maybe 20, 30, at most 100 cycles. And there is a lot of action going on at the surface. We have the feelings, for example, that sometimes, let me say something else. We try to use as little palladium as possible. Mm-hmm. So we're sometimes working with 5 nanometer. What we see then, what happens is that there is an oxide of the underlying film which will creep up the palladium islands and slowly cover them and making them less active. On the other hand, I can tell you that I have a magnesium gadolinium switchable film in my room. It has been for 6 months there, and once in a blue moon I turn the hydrogen on and it is still switching. And it is at open air and so on. I can also tell you that if we conserve our films in a very high vacuum, but not ultra-high vacuum, then it is a disaster. These things don't switch anymore. So there are a lot of things happening at the surface we don't understand yet.
Yeah, thank you very much for that. It suggests the possibility of the measuring the hydrogen in the real state, because we need a very good measurement apparatus on the board. And that's very interesting indeed. Yeah, thank you very much.
Okay, last question from Keith.
Ron, have you considered the possibility of, instead of sputtering, using an electrolytic deposition process? Because presumably very similar processes would occur.
We have not. So far we have used electrolysis only to load hydrogen, because this is another way of measuring PC isotherms. And the other technique we are using is MBE, but that's a rather time-consuming technique. Once you have a sputtering machine, MBE looks like masochistic tendencies.
Okay, let's thank Ronald again.
Okay, so our last speaker for the session is Rosario Cantelli from the University of Rome, and he's going to tell us about monitoring chemical reactions and point defects dynamics in alanates.
This work is carried out in collaboration with a group of Craig Jensen and with the collaboration of Alberto Albinati of the University of Milano and of Marco Zoppi of CNR in Firenze. This is my group where Annalisa and Oriele are very busy and involved in the research on and measurements on alanates. So alanates are offering an interesting perspective as hydrogen absorbers, especially after it has been found that titanium catalyst makes the reaction reversible, lowers the reaction temperatures, and fastens the kinetics. The reactions are written here. You know them very well. We have they occur at progressively higher temperatures, from the tetrahydride to hexahydride, plus segregated aluminium and hydrogen evolution as gas, and then from hexahydride to sodium hydride. And so this takes place at a higher temperature. So the two reactions, this is Jensen and other authors. Sorry, I wrote only the first name. The first reaction has an onset of at about 50 degrees centigrade, and so the second reaction 100 degrees above. When titanium catalyst is present, otherwise in the undoped material, so you see the reaction has shifted drastically to higher temperature. It is not yet known where titanium goes, as in interstitial or substitutional or within the grain at the surface. We have the measurements from Alberto Albinati, Cognes, and Zoppi that give no evidence for titanium atoms in interstitial position, and rather give evidence which slightly favors titanium as a substitutional in the aluminum position. The reversion from decomposition of a solid system is a rather striking event, considering that the solid is ordered in a lattice structure, that the initial and ending stoichiometries and symmetries are very different, so from the tetragonal to the monoclinic, and that segregation of the components takes place, like aluminum in the present case. No explanation is available at present for this phenomenon. but there is a general agreement that the existence of mobile species should be postulated in order to interpret the evolution of the de- and recomposition process throughout the sample. Recently, we observed by an elastic spectroscopy a very mobile species involving hydrogen, which appears during the thermal decomposition reactions and which may provide the key to understand the microscopic mechanism governing this unusual reversible reaction. I must spend just a couple of words to illustrate what an elastic spectroscopy is. Any point defect introduces a lattice distortion represented by a second-rank tensor called elastic quadrupole. The distortion can have different orientation within the lattice, but they are energetically equivalent in the unstrained and unstressed sample. If a stress is applied, for instance, horizontally in the present case of the figure, the green sides are made energetically favored with respect to the red sides. So we have a redistribution among the favored sides, and consequently we have an alignment of the distortions, and macroscopically we observe a time-delayed strain called an elastic strain, which is summed up to the elastic instantaneous strain. Those experiments are most sensitively carried out through the vibration. So by putting a sample in vibration and by applying the external stress through the vibration. There is a maximum in the elastic energy dissipation when at the relaxation condition, when omega tau is equal 1. In other words, when the angular vibration frequency is equal to the relaxation rate of the mobile species. So this measurement gives a direct determination of the jumping times of the atoms through this condition. This is a picture of the experimental set. This is a right analanate sample, and the complex modulus, so the elastic susceptibility we measure, is given by the dissipation, which is measured through the logarithmic decrement of the amplitude or through the resonance curve, and the Young dynamics modulus, which is measured through the vibration frequency. So the modulus is proportional to the square root of the vibration frequency. This is that. So experiments. We carried out elastic energy dissipation and frequency measurements, that is the modulus measurements, as a function of temperature, starting from room temperature and to cycling up samples at increasing maximum temperatures. Cycling up to 360 K, the modulus reassumes at room temperature the same value, indicating that there has been no onset of decomposition reactions. But increasing the cycling temperature, so by 20 K, the modulus, the cycle remains open, indicating that the reaction started. So the elastic modulus is very sensitive to the formation of different phases, precipitates, and so on. And by increasing the cycling temperature, the elastic modulus displays a dramatic softening, indicating that the material is transforming itself into another material. But when a cycle is made at the same temperature of the previous cycle, very little occurs, indicating that the decomposition did not proceed significantly. After each high temperature measurements, we carried out the low temperature measurements in elastic energy dissipation modulus. So after the cycle not displaying decomposition, the dissipation decreases monotonously. When at this temperature, we observe the development of a peak which increased and developed with increasing high temperature treatments. So this peak is rather surprising. Well, how can I go back? No, sorry. How can I go back? Oh, yes, sorry. No. I should go back. Present, ok. Sì, indietro con questo? Ma come vado a prendere questo? Come tocco? Come faccio? Ah, sì. Sorry. Yes, so this, okay. This peak, this one, okay. So this peak is caused by a species absent before the thermal treatment, I showed you. This species is very mobile, as it performs 5 10 to the 3 jumps at 70 K, corresponding to a relaxation rate of about 10 to 11 jumps at room temperature, which is so the dynamics of hydrogen metals. The peak is broader than the Debye peak, than the Debye process, indicating interaction between the relaxing complexes or multiple occupancy. And principally, the pre-exponential factor is typical of point defect relaxation. So this is the activation energy, 0.126 electron volt. So what information did we get from this first set of experiments? A new species enters the field of existence after the onset of decomposition reactions. This species is very mobile, is constituted by a point defect complex, and this point defect complex is hydrogen, as confirmed by the isotope of measurements. So this is an experiment with deuterium, which shows that there is a shift of the peak towards higher temperature. So the preliminary results on isotope effects show that the anelastic process has an isotope dependence, indicating that the peak is due to a H-related complex. Possible mechanism for the low temperature peak. Tetrahydride should be excluded because the peak is absent there. So the possible sources should be searched in the products of reaction: hexahydride, segregated aluminum, and sodium hydride. Sodium, the relaxation of H around sodium in the sodium hydride is rather unlikely because the peak appears as decomposition starts, and this reaction starts at high temperature. The reorientation of H around titanium, or segregated aluminum, or a titanium-aluminum complex, so the answer will be in the next figure. The most likely process is a stoichiometry defect of the hexahydride generating a hydrogen vacancy dynamics. The newest data showed us the following. We repeated the experiments in the undoped material, and the process, the peak, was found again. The peak is very little in height with respect to the doped alanate. Because all the temperature are shifted to higher temperature in the undoped material. The process is then present also in the undoped material. Therefore, titanium is not responsible for the peak. The peak is not due to the relaxation of H around titanium. Then we performed several experiments. One indicative set of experiments is the following. So the peak develops when the temperature annealing is increased, develops and increases. But if annealing is made at a temperature lower than the previous annealing, the peak decreases. So here, if the experiment is repeated at lower temperature when this mobile species has no thermal activation to move, then the peak has the same intensity. So all those results should give us a key to interpret this phenomenology. The decomposition formula generically mentions the release of hydrogen from the formula units during the decomposition reaction and its evolution out of the material as molecular gas. But the variation of the peak height with the thermal treatments demonstrates that hydrogen is present in the lattice, also out of the bonds. So we propose all the models. It is difficult to tell it in a few words, but substantially is this. We must individualize the partners of the that take part in the lattice dynamics. We have decomposition from the tetragonal structure from the decomposition of the tetrahydride into hexahydride. But in addition to hexahydride, we have also stoichiometries, defective stoichiometries. So if one hydrogen atom is missing or more, the other hydrogen atoms can relax and give rise to the process. In other words, we have a vacancy, and the vacancy dynamics is possible. But we do not have only those products. We have in the lattice also segregated aluminum. We have also hydrogen trapped by titanium, because titanium is a very effective trapping center, as we found in metals. And we have also free hydrogen migrating in the interstitial sites in the lattice, which may join the surface, recombine, and go out in form of gases. So the bibliography up to now has considered only the first step and the last step, the formula. So there are very important steps that we demonstrate that they are taking place and should be taken in consideration. What happens when a cycle is repeated at a temperature a little bit lower than the previous one? At those temperatures, I showed you that there is no significant progression of decomposition. Therefore, during subsequent cycle at lower temperature, in which the decomposition reaction did not proceed significantly, hydrogen reaches an equilibrium distribution by enriching the deeper sites. Which are these deeper sites? We observe a decrease of the peak after such a treatment. It means that a hydrogen, the lattice hydrogen in free sites or trap sites, goes back to the hexahydride, to the defective hexahydride, and blocks the dynamics of the process. Oh, sorry. Can I go? Oh. So, now, after re-equilibration, the deeper sites are occupied. And what are those deeper sites? Bond sites and titanium sites are both traps for hydrogen. But the deeper sites are the bonds, because the experiment shows that the peak decreases. To finish, the part of the model we propose is considered by the potential profile for hydrogen. In the undoped material, the activation energy for a hydrogen atom to break the bond, is rather high, of the order 1 or more electron volt. The presence of titanium modifies both the site energy for hydrogen and the saddle point energy, resulting in the decrease of the barrier height necessary for a hydrogen to leave the bond. So in this situation, then we have a lowering of the decomposition temperatures, and in this picture we may have stoichiometric hexahydrides, or we can have also defective hexahydrides. When we have an hydrogen atom leaving the hydride, a multi-well potential is formed where the vacancy can relax with a lower creation energy, the one I showed you before, which is 0.12 electron volt. Titanium is a trapping site, and we also have this. Okay, thank you very much for your attention.
Questions?
If you think that this vacancy plays an important role, I would think that you might be able to control the concentration of the vacancy, the hydrogen vacancy. Would that be an important factor? Have you thought about in your experiment? What I said is that it seems that in your result, the vacancy plays an important role. You know that when you look at those defects, the vacancy concentration that you can change it, in your preparation of your sample. And do you, do any experiment to see that whether that has an effect?
Yes, with proceeding of decomposition, so we expect. So with when decomposition proceeds, we have, you see, we have a development of the peak. When decomposition proceeds, then the concentration of vacancies, the concentration of defective units increases, and the peak increases in intensity.
Okay, thank you.
Okay.
Okay, we're running quite late, and we still need to do the panel discussion. So let's thank the speaker again. So I think we're ready to proceed with the panel discussion, and we'd like to invite the speakers down that from earlier in the session, as well as include some panel members, Don Anton from United Technologies, and Professor Fuji from Hiroshima University, and Raja Sundarasan from IIT Madras. So, you're invited to. You can. It's up to you. Need some panelists. What?
Or do you have to stay up there?
Also, well, if Ferdy's going to leave, then we'll go with Alberto Albanati. I don't know about the others, but I'd very much like, well, the others are more than welcome as well, but if Dr. Mori would also come back, I think he might have some important points, unless he left. you see him? Oh, please, Dr. Mori.
So,
Yes.
let me say some words. So, I would like to comment some questions about the finite size effect influence on the not only kinetics but the thermodynamical properties of nanoparticles. I mean phase stability due to the changing of the size of particles. So this is very interesting problem because in fact there are different evidences and indications which were obtained not only by us in our lab but different scientific groups in the world which illustrate us the phase stability strongly depends from the size of particle. So the main contribution in the given case is chemical potential of the surface. So it means that if we change the particle size, you change not only kinetic properties but thermodynamic as well. So at least one main conclusion would be made if the size of particle is, in fact, is very important key factor. It's possible to weight the strong dependence, phase stability, and phase boundaries versus the function of the size of particles. And in the context of our conference, it's possible to, for instance, to create new metastable phase which do not exist on the stable phase diagram, and in order to obtain new kind of phases, but in metastable phase, and for instance, even for the binary alloys which have positive enthalpy of mixing, it's possible to weight solubility extension. So it means that it's possible to obtain the new kind of materials which have new properties which do not exist on the usual conventional phase diagram. So I tried to just only comment briefly and absolutely agree with the question which was asked in the first part of our afternoon session. Thank you very much.
And I thank you for the additional presentation. So if we may proceed with the panel discussion, I wanted to make a couple of comments before going, and that is there was some, myself included, there was some confusion getting back to the whole point of this meeting, and that, and hopefully one of the conclusions out of the panel discussion is to begin to identify possible projects for the IPHE. So what we're hoping for out of this is the interaction to get us talking about how we might solve the problem. So one of the outcomes is they're hoping to get proposals for IPHE on how we might team together to solve the big problems that we must overcome to solve this storage situation. I think an excellent example of this is what we just saw with Professor Contelli and myself. I knew nothing about anelastic spectroscopy, but he saw me speak once and begin to talk about point defects. His technique is very good and very much aimed at the detection and elucidation of point defects. So this, I was able to take advantage of some very different science than anything I was really familiar with. This has now grown to a further collaboration with a group in Japan doing positron annihilation, which again is another technique I knew nothing about. But this is the sort of collaborations we're hoping to get out of this, and that's the hope that we'll be open-minded and come to understand the different things that we all do and how we all might contribute to the problem and work together. So I hope that clarifies that as far as what is expected of us here and why we are here at this conference. I wanted to begin, though, the panel discussion by raising a point that was raised this morning in Gary Sandrock's talk, and that's about this question of the heat management. And I guess it was not stated so strongly by Gary, but if you then infer from the comments Gary made, you begin to wonder if the whole question of onboard rechargeable is dead because of this heat management issue. And I would like some comments from the panel. It seems like that's what they're addressing in the Toyota effort, one of the things they're addressing. I was hoping that Dr. Mori might kick it off here with a comment about that.
From our experience, heat management is a very serious problem. So we tried first low pressure system, metal hydro system, in 2001. So, but unfortunately it failed because two major weak points. One is external cooling during fueling. It is not easy, especially about liquid connection. Other than fuel, hydrogen only, not only hydrogen, but also additional liquid connection is very difficult for difficult to treat the vehicle for utilize the vehicle. It is one of the serious problem. The second is heat supplying for the materials on driving, especially in cold temperature. So very cold day in the morning, we cannot start. So we have to heat the tank for about 1 hour before starting. It is so hard work for our test drivers. So the reputation of metal hydride is very not good in my company now. So we think it is better to use generated heat in fuel stack is available. This is a better way to heat the materials and the tank, I think. That's my comment.
Oh. Thank you. Any of the other panelists care to comment on this heat management issue? Yes, Don Anton, who recently has actually constructed an allanate tank and is full aware of these issues.
Yeah, a few of the things that we've learned in making our tank and system, and I have a poster in the poster session, which I'll be at today, is that it's really design of the management system is paramount, and you have to balance that with manufacturability of the system. We found that if in our analyses that number of cooling tubes is very important, and so the more cooling tubes you have, but you have to limit it to a certain number of cooling tubes, right? Because you have to be able to manufacture it. You can't have 10,000 of these microchannel tubes in there unless they're designed in a different way. So work in microchannel heat exchangers would probably be very beneficial in these regards. When it comes to standard heat exchange design, I think that we're saying that we're at about a 15-minute recharge limit to be able to make and still have reasonable gravimetrics. If you want to put more and more heat exchange in there, you could probably get it faster, but then you're going to lose all of your gravimetric advantage in these materials. So there's an interplay of design of the heat exchanger and what you're willing to pay off.
Oh, sure.
I was just wondering if it would be possible to develop a derating factor that we could apply to tanks or materials that would be used in tanks based on perhaps the binding energy. So it seems that if the binding energy is going to be higher, then in order to meet 5-minute or 10-minute refuel, you're going to need a certain number of heat exchangers. And maybe empirically we could start to say, oh, well, then we need to derate the gravimetric density by, maybe it's 80% or 70%. And it would be useful to have some kind of rule of thumb. I don't know what would be your thoughts on that. Anybody on the panel or Don?
Well, it would be the enthalpy of charging, right? So you would have to work with that, derate the materials. It's with the chemical hydrides, or as Andreas said very succinctly, that all of these materials that are going to be rechargeable in situ are going to have about the same enthalpy. So derating is not going to be a factor in that regard. I think with your physisorption materials, you will have a great advantage there because your enthalpies are going to be much, much less than the chemisorption state. So that won't be nearly as big of an issue. You'll have your other issues.
Well, it seems that the thing that's interesting about the material used in the hybrid tank is that the binding energy there is about 20 kilojoules per mole. So I was just speaking generally rather than the adsorption materials.
So we recommended the previous presentation enthalpy, absolute value of enthalpy about 20 kilojoule per mole hydrogen. So this is Gary Sandrock presented in the morning total amount of the energy, total amount of generated energy at charging time. So very quite big. So this is the limited acceptable level for onboard charging. But if not choose the off-board charge, it is not the limit. I think that is other way. Some possibility to other way. Some possible ways may possible, I think.
But if I may say, but to optimize heat transfer, it always has to be done at the cost of gravimetric efficiency. You've got to put in more heat transfer mass. That's unavoidable. What you say is absolutely true. I mean, we've made small experimental systems where lanthanum nickel 5 could be charged in 1 to 1.5 seconds. But they were so loaded up with metal ballast to hold the heat and so much heat transfer fins, they would be ridiculous as an engineering design. So whenever you decrease the time, you're always going to do it to some extent at the expense of gravimetric capacity. I think that's why your system has only 1.8 weight percent. You've got a fair amount of heat transfer in that system.
Your question is quantity of heat volume is so large too large to release.
My comment was simply that it's always possible to get rapid charging if you put in enough heat transfer surface area and material. You have to have heat transfer material, fins, foams, whatever. And the more you put in to increase the heat transfer rate, the lower the weight percent has to come, because that's dead and inert material.
I think
It's a trade-off. It's a trade-off. You can certainly get, I think, I could see a design that would get charging in 3 minutes, but it would be an expensive system because of all the heat transfer.
I think there's a question behind. Yes.
Maybe one aspect to mention here, the cyclic properties of the storage media and how fine it is going to be after a certain number of required cycling. The other issue in connection with what is being discussed, this storage tank problem, and if the heat extraction is not sufficient, what happens when the overheating is a case where you can destroy the whole capacity of the material? Any comment on that? Then?
I suppose you're referring to a situation where the alloy, when it gets hot, is subject to disproportionation. It breaks down. There are some fairly stable materials, no matter how fast you charge and no matter how hot you get them. Within reasonable limits, they're fairly stable. As far as particle size, heat conductivity is rather independent of that because it's just sort of irregular particles. There's not much actual metal-to-metal conductivity. Most of the conductivity is by the hydrogen gas. And what happens when you get too fine, you certainly increase the conductivity, but then you have problems with gas impedance, pressure drops in the system, which is equivalent to reducing thermal conductivity.
I think we have a comment from another comment from Toyota.
The comment for the hybrid tank seems to be a little bit, how can I say, we request the many requirements for the material. We want lower entropy, high volumetric the capability or high gravitic absorption capability for the material too much. What we would like to present in this Mr. Morris' presentation is we will treat the heat around 2 megajoule per minute of the heat treatment in a real world, because it seems to be quite difficult if you treat the 2 megajoule heat on board. But what we presented is we demonstrate the possibility of having a vehicle to treat such a high heat transfer in a real car. Of course, the smaller the better in terms of the entropy, but we may have some engineering solution that we would like to encourage you to find a better material which contains more. If the entropy can be higher, we will try to solve it. That's the message we'd like to say. And also for the heat control, the most important thing is that you mentioned the physical property of the material, such as heat conductivity or say physical property of the alloy itself. Sometimes it becomes a particle when the material absorbs the hydrogen. So the real difficulty is in those small particulates stick to the bulb, and it stops the function of the prevents the function of the bulb and so on. But at the same time, we demonstrate that we are able to handle those issues. Please take this as a positive the message from our industry.
I think it's good to end this on a positive note, and we'd like to move on to another big issue question. This I'm trying to read it, although the font is very small. It came from an email from Andreas. It says, future cars will have to run with an energy storage system based on hydrogen, which offers less than half of the volumetric and gravimetric energy density of today's gasoline tanks. What does this imply? This kind of touches on some of the things Scott Jorgensen was saying in his talk this morning, and again, to kind of do a caricature paraphrase, he was kind of saying that the public will not embrace small cars. I think, though, we once heard that out of Detroit once before. So anyway, I think we can take it from there.
I'd like to leave a couple of points for us to mull over in this regard. Generally, when there is a trade-off, when there is a discussion between the designer of a system and a designer of a material, there are a lot of trade-offs. Let's take aeronautics, for example. The material requirement there is some of the highest among all engineering requirements. So when they want a system with a material with such high properties, the materials person turns around and says, this is what I can give. Please go back to your drawing board. So the negotiations go on and something is arrived at. I think we should look at it that way. We shouldn't let Sunita give us an edict saying this is the amount and we will stop at this. I think we should negotiate with the manufacturers and of the automobiles and say that. The second point that comes from this is that we seem to be fixated on a car with an intercity transport requirement of 500 kilometers. Why that? I'm not very clear. If we take most European and most Asian cities and many European cities, a lot of transport takes place by bus within the city. I have done a survey in our country, and I find that the buses run perhaps 250 kilometers in the day and spend 8 hours back in their shed. And second, and during which time it is in their shed that they get maintained and get refueled, which gives us an option to develop buses which will run within the city for short distance, low weight % hydrogen, and no need for far-flung hydrogen supply points. And I see on the whole that would be a direction in which things can work much more easily. Thank you.
Oh, Bill, way in the back.
Craig, I think that's the issue of the half storage density is what also then puts constraints on why you may need a fuel cell as opposed to an ICE long term, because you've got to pick up the efficiency then in the fuel cell as opposed to the ICE, so they balance. So if you have half the storage density and twice the efficiency on the fuel cell side, then you're back to about the same platform.
We are not looking at between fuel cells and IC engines. Any one would be fine, but we have to work towards the fuel cell through IC engines perhaps, because at this time there is no question that the fuel cell is the ultimate answer. There's no question about that. But that still does not preclude us from looking at slightly lower targets in terms of distances covered between refueling and in terms of refueling points, distribution points for the fuel to be arranged. We must also recognize perhaps that we are looking at not an economic issue, but an issue of, shall we say, life and death for not us, maybe 3 generations, 4 generations down the line.
Okay, well, we've had some comments on these issues, both of which are, in my mind at least, rather engineering in nature. I'd like to now turn to maybe some suggestions on research that ought to be done to overcome obstacles. We already heard some about the possibility of and the frontiers on I guess it was encapsulated in nano sizing of things. But I wonder if we might get some input from the panel as per where they see the research frontiers on the problem. Anybody? Tell us your own frontier then. Silence.
Okay, Craig. I think obviously, and we've heard from many of the talks, that people are looking for new materials. I mean, we need material that has essentially 7.5% weight of hydrogen, which can discharge, at temperatures like around 100 degrees centigrade and charge either on board or off board in a reasonable amount of time. So, much of the work that we heard today and much of the work that you all are doing out there, I'm sure, is aimed at finding these new materials. Sodium aluminum hydride, which in my opinion is the best material out there now to meet those requirements, is certainly not going to be the final answer. And it's only, in our wildest dreams, 5.5 weight percent. Right now we can probably only pull off about 3.5 weight percent reasonably under reasonable cycles. So, new materials have to be found.
No, I see, we all recognize that new materials must be found, and I think a lot of us are doing prospecting, but it's wonder if we can't do more intelligent prospecting, and what information would we need that would help us in our search for these improved materials, and are there things we could do in our research to again, make our search for these materials a little more intelligent.
Yes, this afternoon we hear the very interesting talks about many complex hydrides, and I think since 2002, Professor Chen discovered the lithium nitrogen hydrogen system, and then start many metal nitrogen hydrogen systems. 4 groups are now concentrated to make new materials. The one is of course Chen's group, and Sandia's Ruo group, and Tohoku University, and Orimo group, and Hiroshima University group, and lithium, magnesium, nitrogen, hydrogen system. In that case, 6.58% is absorbed, and maybe it's, some dynamic properties are very promising. It's below 100 Celsius degrees, the adsorption pressure is higher than 1 bar. And also recently the mixing effect is just Dr. Sandrock talked about the aluminum hydrogen 3 and lithium hydride, the complex, and to make a very beautiful desorption behaviors. Also, we also studying the hydrogenated graphite, and also the mixing with lithium hydride, and 8 to 9% dissolved, and the starting point at a little bit higher, but 200 Celsius degree, and that's reversible, and 5.8% is dissolved less than 300 Celsius degree. So I think now it's a very, very, very interesting to the mixing effect of the lithium borohydride and lithium amide systems, and mixing, and new interaction appeared, and the level is becomes lower than near the. Of course, the lithium hydride is very stable, but the making the new phase is near around this energy delta G state. Yes, so it's also one of the possibility to new materials. So I think it's 9% of hydrogen is also not so impossible, I think.
Oh, okay. I had a comment about your comment, but I think before I do that comment, Carol has something she wants to say.
No, do your comment first.
Oh, go ahead.
I was going to change the subject, so go ahead.
Oh, I was just going to say on that, of course, and we saw in in the presentation, especially in Ping Chen's presentation, was of course the amides are looking promising, but there's a kinetic problem there, and there's a big gap in fundamental knowledge what you might do to improve the kinetics of it. And that's because you don't know what it is that you want to make faster because you don't understand what's going on there. So I think what I guess I was driving at is there's still a need to probe these things on a very fundamental basis.
I think a very interesting comment was made at the very beginning of the panel discussion concerning size. Those of us heavily involved in the science, nanotechnology area feel that there are literally millions of new materials right under our noses, that we can change the thermodynamic properties away from what the conventional thermodynamic properties of materials. For example, if one goes to quantum dots just to take one example, quantum dots of gold and silver. Very interesting work was published in Germany about 10 years ago. By going down to nano sizes, you can actually change the electrochemical potential of gold and silver by about 500 millivolts. In other words, you develop thermodynamically, by going smaller, as has been very well discussed when dealing with quantum dots, one has a whole intriguing new enormous number of potentially new materials. Taking old materials, making them smaller, you develop new thermodynamic properties for them because of the increased importance of surface free energy as a contribution to the free energy of the macroscopic form of the solid.
But let me illustrate with a case from the alanates. Take the alanate and say that you do nanosize it. You got a nanoalanate, and then you desorb it. The thing is, it's going through, and as it cycles, it's making whole new structures. And then when you rehydrogenate it back, how do you control it when you hydrogenate back so that it's nanosized? You can control it at the first place. You can make it nanosized, but as you cycle it, how do you keep it nanosized? There's a problem that things crystallize.
Right. I have no answer to that. But I think that this is something that we should all consider, even though we can't right at the moment.
I don't mean to say no. I'm just saying that there is a frontier there, and there's a thing that we have to control. It's not as easy as just nanosize it in the first place. You're going to have to think of how, and as far as I know, people can't do that yet.
Right. I agree very much with you. A lot depends on rate of cooling, for example, grain size, grain boundaries, domain size. Many problems, but purely when one is talking about new materials, if you can change the standard electrochemical potential of gold and silver by half a volt, you're getting thermodynamically a new material. Whether that concept can be useful in any practical way concerned with the hydrogen economy is a completely different question. But purely talking about new materials, gold and silver, well substantiated quantum dots get a very big change in thermodynamic properties.
Okay, Carol.
I have a question for a panel on their opinion for another potential showstopper. It's not clear whether thermal management is, especially during refueling, but I was wondering, what's the panel's view on understanding how specifically a metal hydride system responds dynamically? Because I could think, how would you understand if it could sufficiently deliver the load for either an IC engine or a fuel cell? And for example, how does it behave as it is literally discharged? Are we going to for example, have a system that we can only empty halfway because after that the material operates in such a way that you can't get hydrogen out of it anymore under conditions that you could put under a car. I was wondering what the panel's view of that as a potential showstopper.
I'll adjust that a little bit, Carol. First off, that's an area which is extremely rich in IP. When you start talking about system designs and how an actual system would work, I think all the commercial companies are going to probably not say so much because you can see a lot of IP delivered out of that. I think that those are engineering issues which, if we thought about them very hard, that we would be able to come up with a number of different solutions which would probably fulfill those requirements. I mean, we already have some written up already, so I'm sure Toyota has theirs, General Motors has theirs. Everyone has their own approaches to the same problems. But I think they're more engineering problems than fundamental problems.
Oh, sure, Mike.
Could I just comment on that? I was wondering if if you hybridize the fuel cell system with perhaps electric battery, then you could do a lot of load leveling and things and get some more dynamic response. I would think that would be a place that most people are thinking about going.
Maybe I can be the right person to respond to that, since I worked also for the hybrid vehicle development. That's true that the hybridization of the vehicle enhances the efficiency of the vehicle, and since we can reduce the amount of the hydrogen storage. But at the same time, there's the vehicle, how can I say, specification of vehicle performance, right? We cannot expect a lot from the hybridization of the vehicle, that because of the conventional vehicle will be improved in the future. So I think the difficulty of the certain presentation that the people compare the requirement of the current requirement and the future fuel cell vehicles. We have to compare carefully the vehicle requirement in the future and the vehicle requirement for the future of the fuel cell vehicle. That in this case, that we set certain target, so that can be a little bit less than normal expectation. But anyway, we will do that. The kind of hybridization, so will be in a normal or 100% option in the future. This has to be thought when we set the target.
So we hope to have many chance to discuss with many researchers in here. So success story is different from each materials, I think. So I want to discuss about the target performance of specific about each specific materials. So what to be developed, or what is the advantage or not. So I would like to discuss first about the target of each material. That's my comment. Thank you.
I think we had one. Yes.
Yes, I want to make a comment on these targets and type of vehicles. I mean, you were talking from IIT on the buses. There are some hybrid vehicles. There are other ICE engines and fuel cell. And I think, for example, in the Store High European project, we try to address these 4 types of vehicles, make a kind of a model type of each category of this vehicle to have specific target for them, because I think having common targets in material science, okay, but when you come to the tank, and the dynamics and the refueling time and all these aspects, it's very much depend on the usage and on the type of load and on the type of distance that you have to cover. For example, the concept of a so-called range extender, which is a hybrid vehicle where you can have 200 kilometers on the battery and then you just need to extend it with the hydrogen, is a totally different concept and with much less burden on the way you want to store and the discharging aspect, charging, discharging. So I think in that, if we refine this kind of analysis, we will give room to more innovation using this different type of material.
So I have a couple of questions or considerations concerning the research directions. Of course, we are happy to continue studying the mechanism of decomposition in ammonites, that is something that fascinates us because you consider this is a solid system. If for a liquid system, it is more conceivable. We know that for liquid systems, there are reversible reactions. Also in the organic matter, there are reversible reactions. So a protein, if you put a protein in a reduced solvent, the protein opens. The contacts are lost. When the solvent evaporates, so the electric force recognizes how to fold the protein again. In the solid system, this is something even more unusual, as everybody understands. So we will go on that. But in the looking for new absorbers, I have a question for the people, if any, here that work with metal-organic frameworks. So they are organic materials mixed with metallic metals, and so the structure, there are nanostructures which are self-consistent also when they are empty of any gas and so on. So the structures, these voids are rather big, so one could think that this is ideal for hydrogen, because hydrogen we could trap many molecules in this big void, but it is not the case. At the present state, the MOF absorb maybe 1% of hydrogen. One possible answer is that hydrogen wants to be trapped. So therefore, make interpenetrate MOFs so that there are more interstitial sites, because there is some sort of bureaucracy in the world of atoms that the heavier atom traps the lighter atom. So I studied niobium, titanium, oxygen, and hydrogen, so solution. So titanium traps oxygen, but oxygen traps hydrogen, and titanium traps hydrogen. The other is the particle which is trapped by every species. Now, this is a way that we should people should investigate in order to increase the massive capacity in MOFs, which may be very promising. The second thing is carbon nanotubes that at the present state do not seem so promising as they are now. So by chance I read a theoretical paper claiming that if you include titanium, so in carbon nanotube, the trapping capacity can be so high that the carbon nanotube becomes promising. So I do not know whether somebody tried this. I would like to ask people about if there are any about MOFs. Maybe Michael can tell us if what does he think about trapping titanium on the surface of carbon nanotubes. And lastly, I would like to make a remark. The big difference, which has been pointed out by him this morning, but other arguments, the big difference between metal hydrides and compound hydrides. So in the compound hydrides, hydrogen is in the chemical bond. In the metallic hydrides, hydrogen is in interstitial size. This makes a big difference. It's not part of the chemical bond, and precipitation means that the hydrogen-hydrogen interaction becomes not negligible. The second hydrogen atom coming will, so when the concentration increases, then the incoming hydrogen atoms will assume the direction of the elastic quadrupole, the distortion. So there are, within the lattice, domains are formed which have the same direction of distortion, and for this reason the hydride precipitation in metals is called ferroelastic transition, in analogy with the ferromagnetic transition. So the zone vice zones are zones where the moment is aligned in the domain like that. So this is a difference that should always be kept in mind. I'm waiting for the answer, the possible answer for MOF and the carbon issues.
Well, but I think we've kind of began to stimulate some discussion, and everyone should keep talking. It's easy to do these proposals for the IPHE. I discovered today I did one, and I didn't even know it, and Sunita told me it was accepted. So it's not that big of a pain to do these. And I'm trying to leave some time for the poster session. If you got a quick comment, of course, Professor Suda. Yes.
Okay. Maybe this is a kind of a question to the people engaging in the material development in general, not limiting metal hydride. Most people don't want to talk about the safetiness or safety aspect of the materials, and also the poor surface properties against water, vapors, oxygen, and sometimes we have to expect the phytophoricity of the materials. So how about your ideas about the new materials, of course, including lithium, nitrogen materials, and also the mineral hydride? We couldn't solve the problem, the surface problem, poisoning effect, the surface. Maybe Gary Sandrock also thinking almost the same things with me. So please give us your comment or ideas about the safetiness.
Actually, please give it to Professor Suda in private, because the boss has given me the sign that we've gone over. We have to do the poster session and then get to dinner. So I want to thank all the panelists and everyone in the session today.
An announcement for tomorrow session will start at 8:30 in order to have more time for the poster session tomorrow evening. The minister will come at noon. So from 8:30 to noon we'll have the standard session. Thank you very much. No, stasera non si possa più cambiare.
I'd like to make one more announcement. If you're presenting tomorrow in the first session and you have your presentation handy, if you could bring it up to the front so we can load it onto the computer, that would be a big help. Do you have your presentation with you, maybe?
Thinking of the fear I
Good morning. It's a real pleasure to have this opportunity to share with you some recent results from our laboratory. I'm going to take a little bit of liberty and apologize up front. I have two abstracts in here. This showed up as an abstract for a poster and also as an abstract for a talk. So the poster abstract is what you have there, and I thought so you get your money's worth out of this, I'd talk about some unpublished stuff. The stuff that was in the poster was the ammonia borane work we've been doing on the scaffold material. This is some unpublished work from our group that's looking at the mechanistic side of things. So I'm going to instead of stepping away and taking a bird's eye view, I'm going to step down into it and try and get some fundamental questions answered about how hydrogen's released from this particular storage material. There's been a lot of talk also throughout the week about how this is an interdisciplinary approach to solving these problems. I think that goes all the way down to the fundamental level of studying these materials, and I'm very grateful to my colleagues. My background's physical organic chemistry, and my colleagues here involved material scientists, computational chemists, and chemical physicists that really helped to sort of get a good start of a picture of how hydrogen is activated or released from this particular storage material. It is sensitive. Okay. So ammonia borane is isoelectronic with ethane, and so but that's about where the similarities end. It stores a similar amount of hydrogen from a theoretical standpoint of about 19 weight %, so molecular weight's the same. But then you start looking at the other physical properties, and it's a completely different beast. The ammonia borane's a solid at room temperature. It melts at over 100 degrees. The ethane is a gas, of course, and you have to cool it quite a bit to make it a solid. And from a chemistry point of view, the bonding is quite interesting in the ammonia borane, in that the non-bonding electron pair donates into the empty p orbital of the boron to make it this dative bond, which is weaker than a covalent bond, but it's greater than conventional electrostatic hydrogen bonds and such. It has quite a substantial dipole moment, and the bond length's about 10% longer for that BN bond. And so that's sort of interesting in the starting material. We're interested in what happens to that bond length as we go to the product, and our computational MACHIC is looking into the change in these properties. So a lot of hydrogen, 19 weight % for the material. The molecule has been was first synthesized back in 50 years ago, actually, in laboratories at the University of Michigan. And it wasn't until quite recently, actually, just 6 years ago, that the structure of it was actually determined. And Crabtree and co-workers got a neutron diffraction spectra and showed what previously the borons and nitrogens had been switched around, and so that they thought this was a real anomalous molecule. But this was named, Crabtree called this, it had a special characteristic in that the hydridic hydrogens attached to the boron act as a hydrogen acceptor. So it's sort of a non-classical dihydrogen bond with the protic hydrogens from the nitrogen. So from the get-go, you have some hydrogen that's already interacting with each other, and so the natural question is how does that affect how the hydrogen is released from this particular material? So we obviously weren't the first ones to think about looking at this. There's been some very, very elegant work that's come from Freiburg, from Gert Wolf and his colleagues that have been looking at this for probably around 5 years now as a potential hydrogen storage material. And the material is stable to air. It doesn't flame up. You can dissolve it in water. If you add acid, it starts to decompose. But neutral water, it's quite soluble and quite stable. So, and for transportation material potential, this has the MSDS of this is safe, and you can transport. You can even send it by airplane. I mean, if you look at the alanates or the borohydrides, you have a hard time even shipping that across the country. So. So what the literature report said that there's two. And the nice thing is you can release this in a couple of different steps. So you can go through, heat this up, release 6 weight % with one step, heat it up again, release another 6 weight %, And then there's some reports that in the literature where you heat this up to over 900 degrees and you can release another equivalent of it. But we wanted to focus on accessible temperature ranges here, and so we looked at this in the scaffold material and hopefully had a chance to see some of the poster. The work came out just last month in Agnavant de Chimie, looking at the kinetics and thermodynamic differences between the solid neat material and the stuff that's in the scaffold. But in this, this is our unpublished results, and we wanted to, once we started seeing these interesting differences in the scaffold material, we wanted to try and understand a little bit more about how the hydrogen is released from this material. So what's the mechanism? It's a solid state reaction. It melts 114 degrees, and it loses hydrogen quite rigorously at those temperatures. So, but you can release it from a solid state at temperatures as low as 70 degrees if you're patient, I guess. Or if you put it in a scaffold, things come off a lot faster. We wanted to get quantitative about this to know what the activation barrier is. So this is when we were doing some of our comparisons. And then, if we know something about the mechanism, the activation barrier, is there some catalysts that we can consider to try and improve the kinetics, or there's some other properties that can be used to enhance the rate for hydrogen release. And are there other products? There's reports that when you heat this up, borazine's formed, and borazine's isoelectronic with benzene and boils at around 50 degrees, so it's not something you want to have in your hydrogen stream if it's going to a fuel cell. So one of the first experiments to do is just to go ahead and kind of confirm what's been reported in the literature. Convince yourself that we're tuned up and ready to go. This is just looking at the volatile products in a temperature-programmed desorption, looking at the mass spec coming off. So you can see the hydrogen comes off in two steps that are sort of convoluted with one another. So this is just a ramped experiment. You can heat it up to temperatures below 100 degrees and just get the first equivalent off. And what's interesting is the borazine does come off with a second step. And so with hindsight, that's probably not too surprising. If you wanted just 6 weight % for a material, then you could just completely avoid the borazine by not going to too high a temperature. And I think I have a pretty picture of the borazine here. But then if you want to get more hydrogen out of this, you got to be more creative, figure out ways to minimize the borazine formation if possible. So when you start digging through the literature to find out how hydrogen is released from this, there are probably about a half dozen papers, and 5 of those papers say it goes by intramolecular or unimolecular dissociation reaction, which is a bit surprising because when you first look at this and you have these hydridic and protic hydrogens that are interacting with each other, you might think it would go by a bimolecular or intermolecular pathway. But there were lots of experiments designed where they tried to trap the aminoborane, this double-bonded olefin species right here, and they were never able to trap it, so they said that it was very reactive, and so you couldn't trap the thing. But alternatively is you never make it because it goes by an alternative mechanism. And there is one paper that discusses back in the 60s about bimolecular pathways for hydrogen release. So this seemed like a pretty simple question that needed to be answered to get an idea of how the hydrogen is released from this so we can start to think about how putting the hydrogen back in. So the simple experiment is to do some labeling experiments and look at the volatile gas materials that are coming off. So just the litmus test experiment, I guess I'll call it, is to look for mixed isotopes of hydrogen coming off from this material in a solid state reaction. So what we did was we can make this or you can buy this from Aldrich, and we can deuterate the material or make deuterated material. And so the concept is to make a homogeneous mixture, solid mixture of a per-proteated and a per-deuterated species. If it goes by a bimolecular reaction, we should see all these different isotopes, HD, H2, and D2, depending on how well it's mixed, kinetic isotope effects. We can, if it's a unimolecular reaction, we should never see the mixed isotope. It should just eliminate H2, D2, and then polymerize and give you the polymeric species that comes off of there. So here's my cartoon slide. Here's a physical organic chemist's approach to synthesis. The ammonia borane itself could be synthesized quite easily. There's other ways to do it, but this, if we want to get the deuterium incorporation in here, the simplest way, you can bubble ammonia through a BH3 etherate solution, and then just excess ammonia, remove the solvent when you're done, and you have ammonia borane. A very clean, pure way of making it. And fortunately, you can buy deuterated boron THF and do the same process and get deuterium on your boron. You can make put the deuterium on the nitrogen just by, it's very labile. You can exchange it with D2O washes, do that a few times and wash all the hydrogen out. And then the last one that we really want is for deuterated is just to start with the deuterated THF and then exchange that. So we have all four of these samples here now so that we can go through and see what the reactivity of these things are. So we need these for fingerprints for control experiments, but we're going to make an intimate mixture again of the ammonia borane and the per deuterated species. So one of the things, the controls that we were concerned about is that there's a report that ammonia borane, it's exchangeable. So if you throw in other amines with this, you can get exchange over a course of period of time that there was no kinetic studies done. So the one concern we had is that we wanted to make sure we had per deuterated, per proteated, and we did not have the mixed isomer of the species. And so the concept was to dissolve the ammonia borane proteated in one beaker, the per deuterated in another beaker, mix them together and rapidly remove the solvent, and then have a near homogeneous solution. But if there's exchange going on in there, that's going to ruin the experiment, because now we'll have, if we get HD, it could be coming from the isomer generated in situ in the exchange. So we talked to our Raman spectroscopist, and so she was able to look at the solids of all these materials. And since nitrogen and boron are relatively light elements to begin with, if you put deuterium on there, you can significantly stretch the BD stretch. And so you can look at the Raman spectra of this and get a fingerprint of each one of these species. And so the idea is then to kind of focus in on this BN stretch area, and you can see both the B10 and B11 isomer, as you'd expect. And when we focus in on that, we're very fortunate we do not make the mixed isomers. So we have, this is a solid state sample that we've prepared now, and we can go do this experiment to answer this just fundamental question about the mechanism. Are we going to see HD or not see HD? So go back, we're going to do the temperature programmed desorption this time, look at the mass spec, and we're not going to ramp it all the way to 200. We just want to look at the reaction in the solid state. We don't want to melt this stuff and have it exchange. So we heat this up. This was, I think, to 80 degrees, and lo and behold, we do get a substantial amount of the mixed isomer species. So we think this is pretty good, strong evidence that it goes by a bimolecular pathway. So you form hydrogen from the hydridic and protic hydrogens that are in close proximity to each other. Whether the reaction is concerted or stepwise, that still needs to be determined, and we want to get more detail into kinetic isotope effects and then also some Arrhenius treatment of the data. So you can start to draw some sort of back-the-envelope scheme of this thing where it undergoes some sort of dehydropolymerization reaction, and you just keep building the stuff up, and it releases hydrogen with each subsequent step. So what is the mechanism for this polymerization, and what's the activation barrier? And so you go back to the isothermal DSC experiments or with the mass spec, and so what you see is you can take this solid, and we're just going to heat it up to various temperatures, heat it up to 70 degrees, 75, 80, 85. It's an activated process. Add higher temperature, the stuff comes off faster. So can we do some sort of a simple treatment on this to get an activation barrier for this material? And when I first proposed this in front of an internal departmental seminar at the lab, the chemical physics guys showed up, and I said, well, this what we want to do is we want to get some sort of estimate of the activation barrier. We're going to assume that half the reaction's over when half the heat's released or half the hydrogen's released, and we have a half-life as a function of temperature and time, and then we can plot Arrhenius and get an activation barrier. And they said, well, that's a little naive. When you have something that looks, this is a sigmoidal kinetics, it's not a simple first or second order process like you see in solution. And sigmoidal kinetics tell you that from people who are studying crystallization, there's 2 steps to this. There's some sort of nucleation that happens to start the reaction, and then once that happens, it takes off and releases the hydrogen until about half of it's gone, and then it can't overlap anymore. So this rate increases with temperature. It's got this sigmoidal behavior, so that it's indicative of some sort of nucleation and growth process for formation of hydrogen. In the thermodynamics, just to make sure we're on the same page, it's 21 kilojoules exothermic, 5 kcals. That's just what the Freiberg group measures. So this was a nice graph that the chemical physics guys gave me. The box is sort of a chunk of solid ammonia borane. The nice graphic on the other side sort of shows the hydrogen bonding dynamic. And so the question is, do you get some sort of polymerization growth along this way or up this way? And so you can kind of get into some of the details about how this reaction might occur. And I think, so here's, whoops, I did that too fast. So you get this nucleation site that happens, and it starts to grow. And if you get a nucleation site somewhere else, they overlap. And once they start overlapping, that's when the reaction starts to go down. And so because you have these depleted areas of hydrogen. And they introduced me to the Avrami equation. And the Avrami equation for this crystal formation, for crystallization, it has both a rate constant in it for the reaction that you can do as a function of temperature, and this exponent here, n, which tells you something about the growth, whether it's 2-dimensional, 3-dimensional type of growth. So you can fit the kinetic data that we did by just integrating the amount of hydrogen comes off or heat, and get some information about the rate, and try and find out how this polymer is growing. So this is, I apologize for squeezing this all into one graph here. So there's 70 degrees, 75, 80, 85 degrees. The blue line is the integrated release of hydrogen. The black line is the experimental fit to the Avrami equation. The red line is the fitting the Avrami equation with n equals 2. And so we tried it with n equals 3, and it wasn't as good a fit. It's somewhere, the best fit is somewhere between n equals 2 and 3. So it may be more complicated than just a single linear growth that goes on. And so this is something that needs to be addressed and understood a little bit more. But now we have these rates as a function of temperature. We can get an activation barrier. You plot an Arrhenius, you do Arrhenius treatment of this data, and it turns out that the barrier for release of hydrogen from this is about 28 kcals per mole. But this is, you have to remember, this is the sort of the rate limiting step here. This is the nucleation event, because what's important about this is that if you understand what this nucleation event is, that you don't need a catalyst anymore. If you can put if it's a chemical process, so that the first step is rate limiting to make the first BN bond, the rest will just take off from there. Or if it's some sort of physical event, some sort of disorder you get by heating this thing up, and then it starts to lose hydrogen. So if you know those sorts of things, then you can get an idea of how to enhance the kinetics with this here. So sort of the conclusion, just put this, summarize it best, I think, with a kind of an energy level diagram here. We've got an activation barrier of 28 kcals for kind of the rate limiting step for just the starting with pristine material. And the heat of reaction is 5 kcals per mole exothermic. So that's the other interesting thing about this compared with carbon systems, which are endothermic for release of hydrogen. This thing is exothermic with release of hydrogen. And so that's going to make it a lot harder to just pressurize to put the hydrogen back on. But some of the stuff we've done with the scaffold material that we've published and it was on the poster, the enthalpy actually changed to almost thermal neutral. And so we're pretty excited about, we know to kind of demonstrate for the first time that you could just pressurize this and see hydrogen go back on here. And we have a Sieverts apparatus coming from Carl next month, and we want to do the measurement at high enough pressure so we can kind of demonstrate this reversibility. It'll give us some more information about the enthalpy. So bimolecular reaction, not a unimolecular reaction. Kinetic growth, nucleation, and it's somewhere between this 2 and 3D growth. And so the critical question really is, what is this nucleation event? Because then if you have that, you can possibly enhance the kinetics. And so we can seed the reaction and get the hydrogen off at lower temperatures or faster rates at the same temperature. And so that sort of wraps it up. These are a lot of people at the lab that have contributed to this, either intellectually describing, exchange of information, as well as doing NMR analysis. We've been involved with all the stuff we've been doing, and we've been involved with this about 16 months now through internal funding. One of the things we're very excited about is we're part of the P&L is part of the big Chemical Hydrogen Storage Center, and we'll be working. We have 3 different tiers in that group, and so this BN chemistry is really sort of a focus on its own, and it involves Tom Baker and Dave Thorne down at Los Alamos, and Larry Snedden at the University of Pennsylvania, and Mike Heineke at the University of Washington and we're going to focus really on regeneration of these materials with that sort of funding. So with that, thank you for your attention.
Okay, start questions and comment, please.
Yeah, I have a question because you showed one of your slides was embarrassing because there was a diborane coming off, and my concern is about the safety aspect of handling these aminoboranes regarding the emission of diborane, which is very toxic gas, as you know.
Toxic, flammable, yeah. It wasn't on any of my slides. We have not. We see borazine, which is probably not something you want to drink or breathe, but it's diborane. We do not see diborane when this thing decomposes. I think it's pretty hard in the solid state. I mean, you have to break that dative bond a couple of times and have a couple of diboranes come together. We don't see ammonia. We don't see diborane.
No, I'm referring to the slide where you're showing the synthesis with ammonia mixed.
Okay,
yes,
yeah,
and
right.
then there was diborane coming off. So.
Oh no, that was a cartoon. That's diborane going in. So that you can synthesize it from diborane. So there's 2 approaches. If you add excess ammonia to BH3 etherate, you make 100% ammonia borane. If you bubble diborane through liquid ammonia, you end up getting about a 50% yield of ammonia borane plus this diammoniate of diborane, which is a real interesting species in itself. We think that might even be the nucleation event. So that was a synthetic benchtop way of preparing these labeled materials. But in solid, we don't make diborane.
You mentioned that the reaction is exothermic, and at the same time you increase the entropy in the system upon decomposition. Why do you expect that you get it reversible when you just enhance the pressure?
Good question. And that's why I think the mechanism is sort of important to know. We're not just taking hydrogen and putting it into a solid, and you're paying the entropy penalty for taking it from the gas phase, out of the gas phase. If it's actually a bimolecular reaction, the entropy penalty may not be as big because now you're taking a polymer of some sort and you're going to break that in half. So you gain some entropy. It's not going to compensate for the hydrogen, but I think that it will start to tell us whether or not the entropy penalty is less. So for 5 kcals, it's still too exothermic. If it's thermal neutral, near thermal neutral delta H, in which we see when we put this stuff in this mesoporous scaffold, I think there's a chance to pressurize and reverse it. So we've done some more deuterium labeling experiments where we've kind of got some preliminary evidence that suggests that it can go backwards.
Any questions? Okay, thank you very much. Okay, we move to the last one. Approaching DOE hydrogen storage long-term goals by Piero Paolo Procini. Thank you.
Okay, thank you. Hydrocarbon represent the only way to power automobile. At the moment, it's very difficult to to imagine another way to power automobile. But the problem in the case of petrol shortage is very how we can move without gasoline. And gasoline is very important because it's very abundant and low-cost material, and also it has a high energy density, but the problem is the pollution, and I believe that the perspective of sharing another decade with pollution from exhausts from internal combustion engine is not acceptable. Hydrogen car is emerging as an alternative way to power automobile. Roughly speaking, to run about 100 kilometers, we need about 1 kilogram of hydrogen. And to meet market request, about 5 kilograms of hydrogen should be stored in the car. And to meet the DOE technical target, we need high gravimetric capacity, has a high 9%, and high volumetric capacity, and also the storage system cost should be very low, and the system fill time should be as low as 2.5 minutes. To meet the DOE goals, ideal metal hydride should have low molecular weight and high hydrogen content in mole of hydrogen per mole of metal, high density, low reaction enthalpy, and low cost. Now I want to show you the case of lithium nitride. It was shown that lithium nitride can reversibly cycle about 5% of hydrogen at 285 degrees, and we found that doping lithium nitride with titanium 2 mole %, it's possible to cycle about 10% of hydrogen per mole of per gram of lithium nitride. This is this graph shows the pressure as a function of hydrogen content for titanium doped material. The pressure in charge was about 30 bar, and the temperature was about 285 degrees, both in charge and discharge. So it could be a good material to meet 9% weight percent for the system. And the problem is that it has a very high enthalpy. The enthalpy of the reaction is very high, at about 35 kilojoule per gram of hydrogen. And the high value of the enthalpy has several consequences. The working temperature is relatively high. Part of hydrogen has to be burned to allow other hydrogen to desorb, and the parasitic reaction can reduce the hydrogen content to about 70%, and so only about 7% of hydrogen can be stored in lithium nitride. And so it means that it could meet short-term DOE goals, but not long-term goals. Technological challenges are the fabrication of high-temperature tanks working at about 300 degree, able to exchange heat very quickly. And about 1 megawatt of heat should be disposed in 2.5 minutes for a fast refill. This is a picture showing a car refueling very fast and the heat exchanger in the back to remove the heat. Okay. Another way to meet DOE goals is the hydrolysis of hydrides. The reaction of some hydrides with water can represent an affordable method to produce hydrogen, especially if we are able to recycling the water from fuel cell. In such a case, the gravimetric energy density is very impressive. The hydride must be regenerated off board. Among others, lithium hydride and sodium borhydride has an energy weight percent higher than 20%. and it represents a simple hydride and a complex hydride. And we tried to use this hydride, the hydrolysis of this hydride, to produce hydrogen by following the pioneeristic work of Aiello and others, and using steam instead of water to produce hydrogen. We designed this simple reactor in which the hydride in which steams produced in a steam generator arrive in contact with the hydride that is contained in the reactor. The hydrogen and the water vapor arrive to heat exchanger, where water is condensed and hydrogen measured by water displacement. This is a picture of the setup for hydrolysis. We checked the different temperature. The temperature of the reactor and the steam generator can be set independently. And with this, the result of the experiment is that sodium borohydride is very hygroscopic material, and when the vapor pressure, the water pressure is very high in the vapor phase, part of the water pass from the vapor to the solid phase and absorb on sodium borohydride and form a liquid phase. The liquid phase formed by a solution of water and sodium borohydride start to produce hydrogen, but the reaction is difficult to control due to the formation of foam that bring the solution outside the reactor. Also, the sodium hydroxide that is produced during the reaction stops the reaction itself, and so we encountered a lot of problems. In the case of lithium hydride, but also in the case of we obtain the problem that we had, that is the volume of the reaction products is larger than the volume of the parent lithium hydride. So in some case there is a reactor occlusion, and the reaction enthalpy is very high, and so we need to refrigerate the reactor. And other problems, technological problems, have to be solved. For example, the hydrogen is produced at a very high temperature, and it has to be cooled before to feed the fuel cell, and water has to be recycled, and heat has to be used to increase the water temperature to form steam. This is a complete schematic view of the reactor that we are imagining, in which it's possible to observe the heat and water management. So technological problem can be avoided, and the major problem is the cost. Lithium hydride, the cost of lithium hydride is lower than the cost of metal lithium. And sodium borohydride, 60% is related to cost of sodium metal, and to reduce the cost, in the case of sodium borohydride, both sodium metal production as well as a new synthetic way should be found. Roughly speaking, not depending from the kind of hydride, the cost of hydride is about €100 per kilogram. We saw €50 per kilogram in the case of sodium borohydride. To store 5 kilograms of hydrogen in a car, we need at least 20, 25, 30 kilograms of hydride. So it means that we need about 1,000 or 2,000 euro for a full. This could be the situation of the people that has a car. So how to decrease the cost of the sodium borohydride? We saw two ways just this morning. The synthesis of sodium metal starting from molten sodium hydroxide that can reduce the cost of sodium. Or otherwise, we saw this morning the work of Professor Sudandash and Altri. Sodium borohydride can be regenerated from borax using magnesium or other less expensive compound as aluminum or at least carbon, that it could be the ultimate way to obtain low-cost sodium borohydride. We are studying in this direction, but we are only preliminary results. I was very at the end of my talk, and the conclusion is that solid metal hydride can meet some requirements, but not all. And to move to hydrogen-based economy, some technological improvement has to be done. But at the same time, we need a new culture model to be developed. And I believe that at the moment, only revising our style of life, it is possible to contribute to a cleaner environment. Thank you very much for your attention.
Okay, comment, questions, please. You have enough time, right?
Yes, I have a lot of time for questions.
Okay. No? Somebody? No? Okay.
You had carbon down as the source of electrons. Did you say you were working on carbon as well?
Yes, we started to work, but we have not any results to show.
I should say thank you very much for all the speakers.
Yeah. I'd like to invite all the speakers to come up, and we'll start our panel discussion. So our panel has the good fortune of having lunch after it, so it will be a fixed time, we believe. So I think as a prelude to the panel discussion, maybe we can, I'll just review a little bit of what we've heard this morning and where some of the areas of overlap and potential collaboration might be. So we've heard a number of concepts have been advanced for chemical hydrogen storage. There are a number of materials that look like they can meet the hydrogen storage capacity targets. Of course, everyone, I think, appreciates that the entire system will be quite a bit lower density than the material itself. There's a potential, as we heard today, for a liquid or a solid infrastructure even, rather than a gas-based infrastructure for hydrogen storage using chemical systems. Some exothermic and some endothermic reactions are possible, and heat management and controlling those reactions will be important for both concepts. Regeneration will likely be off-board, although I guess on-board concepts can be envisioned, but the focus seems to be on off-board right now. Brings up some fairly interesting infrastructure issues for an off-board regeneration concept that would have to be looked at. There are some of those regeneration concepts that would involve hydrogen, but some of those regeneration concepts will likely not involve hydrogen as a gas, and so maybe those regenerations can be coupled all the way back to the energy source that would have been used to make hydrogen gas in the first place. Energy efficiency of that regeneration is going to be extremely important, as we've seen discussed in the talks this morning. Recyclability of those materials will also be important. We heard kind of three general areas: sodium borohydride hydrolysis, where catalysts and systems for hydrogen generation are important, as well as concepts for taking BO bonds and reconverting them back to BH bonds for regeneration. And one of the themes there was that we may need cheaper or more readily available reducing equivalents or cheaper electrons to do that reduction chemistry. We saw some ammonia borane concepts, where there are now several concepts that are in the posters and were in the talks on how one can get hydrogen to come off ammonia borane. And as Tom Autry pointed out in his talk, I think the next challenge there is going to be how we regenerate those dehydrogenated BN species and how far you actually go. And then we heard several concepts on some endothermic dehydrogenation systems using organic molecules, where some of the theoretical energy efficiencies might be very good for the regeneration. The key there is likely rates and catalysts for the dehydrogenation, whereas the rehydrogenation really falls into systems that the chemical process industry already knows how to handle pretty well. So there's a list of about 7 things that might be worthy of some potential collaboration discussion. These are chemical processes, so catalysis is going to be very important, homogeneous and heterogeneous processes and rates for those catalysts, and some catalyst discovery, particularly for probably non-precious metals to make those catalytic processes go. Coupling of the hydrogen storage system with the fuel cell, as we heard, will put some stringent requirements on the type and amount of impurities that can be tolerated, and what the heat balance, how much heat will need to be taken away or provided for those reactions, mechanisms and kinetics of those reactions. A lot of these systems are molecular and very amenable to theoretical calculations for calculating intermediates, and so that's probably something that can be brought to bear. With respect to onboard reactor concepts, there are likely some opportunities for reactor engineering, simple, robust systems where one needs to control the interaction of the material with the catalyst. There's some examples on the posters on current systems. And from offboard regeneration, probably the energy efficiency aspects, but also the infrastructure aspects. And so with that, I think we can open up the panel discussion. Are there any questions, comments?
From an energy efficiency point of view, it seems that one threshold that you may want to or try to come underneath is those metals that require electrolysis in order to start the regeneration, and perhaps those processes that could be done by other thermal methods, perhaps where the electrons are less costly. It's where do you think we are now and for the different processes?
Anybody want to take that question?
I guess I can give it a try. In our study for looking at various ways for sodium borohydride production, we did evaluate a number of thermal processes, and just to summarize the results, our study actually indicated that to generate the reduction reagents required by thermal process are actually also very energy intensive steps, and in the end it doesn't really come out ahead of the electrolysis processes. People mentioned a lot the sodium, magnesium, and aluminum as 3 metals that used to be used as potential reducing agents, and all 3 of them you can find ways of making the metals both thermally and electrochemically, and if you compare the energy efficiency, all 3 of them come out with the electrochemical process being more efficient.
Additional comments, questions?
I have a comment. I'm a boron chemist, and I think the regeneration of the compound of borohydride are only commented for a long time by an old method. We are always trying to do very hard method to change boron oxide to boron hydride. I think boron chemists have to look to other methods, especially a soft method, which has been developed for a lot of chemistry and not for us. And I asked my colleague from Japan, because there is the meeting of boron chemistry this year in Japan, to ask to their colleague what can be new in new chemistry of rehydrogenation or changing from oxide to hydride on boron chemistry. I think something could be done, and we are changing for very few and very few changing sodium for magnesium and so on. If the process are more efficient, that's right, but the end of the purpose is the same. So I think we have progress to do, but in a larger way of chemistry.
I guess I'll add to that just a little bit. There are a number of metals, obviously, you can choose as reducing agents, but in the end, it's limited by thermodynamics. The redox potentials have to match the reducing power of the reagent has to be enough to break the boron-oxygen bond and change the oxidation state. So that's what I want to add.
I think you can think of that two ways. One is once you make a boron-oxygen bond, as you said, what are some other concepts that might allow you to manipulate that boron-oxygen bond as opposed to a direct reduction? And that's certainly something that I know in the Center of Excellence that we have for the chemical hydrogen storage, that's one of the tasks that we've set out to do collaboratively with groups like Roman Haas and Millennium Cell and some of the other collaborators. The other question that it bears out, of course, is how to get hydrogen out of these very appealing, very hydrogen-rich boron systems, but never make a boron-oxygen bond and fall into a deep thermodynamic well in the first place. And that, again, of course, is the other challenge, and we're seeing some indications in some of the other systems, like the ammonia boranes, where we might have a different thermodynamic balance.
It seems that if you need high temperature and lots of electricity, I would guess this process, or some of these processes, might fit well with nuclear reactor electricity. If CO2 is the thing that we really want to avoid in the long run, I think even environmentalists such as myself will have to embrace nuclear reactors as part of the mix, at least in the U.S. Just a comment.
Well, I think staying on the technical end as opposed to chasing that dog right now, I think one of the opportunities, as we talked about maybe, is the possibility. We have to realize when we make hydrogen, when we transport hydrogen, there are energy efficiency issues there as well. And so some of the opportunities might be to back up to that energy source and not go through hydrogen in the first place. And so if you can do that, you have an opportunity to get some credits for energy efficiency on your regeneration process that wouldn't exist in other cases where you used hydrogen. So it's a balance, I think. A comment, Professor Su?
About application of electrochemical reaction or application of thermal decomposition or thermal synthesis. But our point is not located to the electrochemical or thermal reactions. Just we focused our attention on the very active surface, surface excitation against the molecular molecular hydrogen. This is very easy to be decomposed at the extreme surface of metal hydride. So it is a good chance to make use of decomposed, it is not the monoatomic hydrogen, but it is a so-called proteid. So we are going to make use of such kind of very active condition state of hydrogen for synthesizing some kind of, like our sodium borohydride. We can save the energy, so-called about Andrea's question that I didn't answer about that through some reason. But anyway, energy level is very low because of its own self-containing energy. Excited condition is very, very important. So and we have now undergoing a project of how to make use of the excited conditions of the hydrogen and also mineral hydride surface. So I don't think it's a mineral hydride the application is good for hydrogen storage. No, I think it's the catalyst and also the electrode with the good surface. So we have I think such kind of ideas. Okay.
Yes, when we started thinking about the Chemical Hydrogen Storage Center, we were really concerned about that issue and the regeneration, so we diversified our approach to that. And as Bill was mentioning, to try and one of our 3 tiers is to just avoid the BO bond formation by looking at these BN bond materials. And I wanted to take an opportunity to say that we're not the only ones doing this. Mark Bowden had a poster on some of the stuff where he was putting substituents on the ammonia borane, and I think we're real interested in that and how that changes the thermodynamics. The neat reaction itself is 5 kcals exothermic, and it is one of the questioners pointed out, that's still too exothermic to just pressurize with hydrogen. We've gotten it up to 0, and we're trying to understand how that happens. When we put this stuff on a mesoporous scaffold, we have some ideas with that. But if you can have substituents that change and you can dial in that thermal chemistry, then you might have something that you could possibly regenerate on board, or in the best of circumstances, you don't have that. We look at it just a simple, it's 5 kcals exothermic versus the hydrolysis, which is 60 kcals exothermic. So if you're going to have to put energy into the system, it's a lot less energy intensive, just from maybe that's an apples to oranges comparison, but it's at least you're not starting way down in that well there. So I think there are people that are starting to look more at these boron nitrogen compounds, and then also RTI. I think they have a group that's looking at synthesis of the ammonia borane in Russia, and I'm going to take the diborane out of my slide presentation because I think that leads to some confusion. I mean, that's not the way we'd recommend making it. It's just a synthetic procedure to get there. So, but I think that alternative ways to get the hydrogen off these borohydride-like species are attractive thing to look at. And the way we really got started in this was we have a very strong computational group, and the group I'm in is half theorist, half experimentalist. And the question was raised by my theoretical colleague Maciek Witowski. He said, well, why is everybody putting hydrogen only on the anion? Why don't they put it on the cation? And so he called me up and said, why don't people look at ammonium borohydride? And so that's how we sort of got started looking at this. And ammonium borohydride was made. It loses hydrogen. It's unstable at room temperature. And so issues, that's isoelectronic with methane. That's 24 weight %. So there's the thing we like about that. There's 4 different steps you could envision looking at for these boron nitrogen compounds, and so that's sort of what we focused on with the Chemical Hydrogen Storage Center, and with emphasis on regeneration. We think that the first 2 steps we looked at, the hydrogen comes off pretty low temperatures. I mean, you can get it off. The first one you can get it off at 60 degrees with a scaffold material. And then I know Los Alamos is currently doing some stuff with catalysis that has it coming off at room temperature. But I think that's the alternative, is looking at other borohydrides that you don't do the hydrolysis.
I just wanted to mention one other issue with the hydrolysis type reactions, how sometimes it's assumed that the water would be available from the fuel cell. If that's not the case, then the additional water would have to be included in the system calculation for weight and volume and so forth. And of course, the amount of water available from the fuel cell can depend on many factors like the operating load, external conditions. And I wanted to call on some of our industry participants, maybe Tarek from Daimler Chrysler, if they can comment on that.
I guess at Daimler Chrysler a couple of years back, we built a minivan called the Natrium,
which ran on sodium borohydride fuel, a 20% solution similar to what was presented today. Just to maybe add one note to what was asked before, the potential for a thermal runaway as a fuel is just sitting in the tank. I can say for sure that we didn't have any kind of problem of a potential thermal runaway. We had our tanks sitting in the vehicle, sitting outside in the parking lot for an entire day at times in very hot summer conditions, and we didn't have such a situation. I think there is enough excess water in the system to prevent, a thermal runaway. We did have obviously some hydrogen evolution, but we were able to deal with that fairly easily with a catalytic burner in the tank. So that wasn't a very big concern to us. The other thing we looked into quite extensively was the amount of potentially recycling some water from the fuel cell to try to improve our overall gravimetric density. One thing that you find in automotive fuel cells particularly is that the amount of water available to you is much less than you would theoretically think it is. On average, you get between 30 to 40% of the theoretical amount of water that you can condense on an automotive system, given that most condensers are operating at the low temperature coolant of around 50 degrees Celsius, so it really limits how much water you can condense. If you want to condense more water, it usually comes at a big penalty in terms of heat exchanger sizes and condensers, which should be assumed to be part of the weight of the storage system. So it's very difficult to retrieve significant amounts of water from a fuel cell.
If I may add to that just a little bit, I think there are two places really within the overall system where you can have opportunities for recovering water, and one is, as you mentioned, from the back end of fuel cell, and really you can only account for a small percentage of that water produced at the fuel cell. Another opportunity is really, it's immediately post a catalytic reactor. There's a lot of water of condensation that you can recover and use again. And in fact, for practical solution concentrations up to 35%, you can use that part of the water to incorporate in the recycle loop, and without having to recover any of the fuel cell water to improve your system efficiency and storage efficiency. So it's only when you push the fuel concentration above 35% or higher, then you need to start looking for other places to get water from.
If we could entertain a slightly different question along the lines of the point that Alan McDermott was making to Alan Cooper's talk about incorporating perhaps something that might be catalytic directly into the molecule, the generic molecule that might be hydrogenated. It kind of ties up into this boron discussion as well, because in the DOE's Center of Excellence for Carbon-Based Materials, we're looking at boron incorporation into different kinds of graphitic and nanotubular materials. And some computational chemistry done by Shengbei Zhang shows that a boron species can act, localize a hole, and participate in this non-classical dihydrogen bond, much like the transition metals do, with an elongated hydrogen bond. Now, normally we think about that as being advantageous from a point of view of physisorption, but that elongated bond is it's a hydrogen, a dihydrogen stabilized in like a transition state towards perhaps being able to hydrogenate the carbon around it. So I wonder if that's just a pie in the sky idea, or if there might be some possibilities there.
I guess I wanted to also kind of understand more what Professor McDermott was talking about is the metals. Is like a homogeneous reaction, or it's not like you want to have a metal for every organic compound in there, or is it?
Well, I was suggesting a boron substituted right into the carbon lattice, and that boron species acting perhaps a little bit differently than the nitrogen that Alan uses in the
Yeah, I think you have to be extremely sensitive to adding any weight to the molecule that's not productive weight. You're always striving towards 1 hydrogen per heavy atom in the molecule, if that heavy atom's carbon or nitrogen or what have you. So I think we're always going to be limited to having something that's truly catalytic and can be present in extremely small amounts on the molecule. But I appreciate what you're saying. If you could add a functionality that's relatively light, containing boron, then you'll dilute the hydrogen carrying capacity a little bit, but if it gives you a big boost in performance, it might be worth it in the long run.
If you could simply substitute the boron for the nitrogen in your compound, you'd get weight savings, and you'd have all the carbons there. I don't know if that molecule exists or some analog exists.
Yeah, that molecule exists. It just turns out that the thermodynamics go in the wrong direction in terms of heat of hydrogenation, so it actually hurts you from that perspective.
Yeah. See, I'm somewhat interested with the organic, carriers, liquid carriers. Well, according to what we worked before, we thought if a liquid can be catalyzed to be hydrogenated or dehydrogenated, directly in the liquid state, it would be very easy to use the present infrastructure. Just to carry the organic liquid there, if we pump just send the hydrogen to the fueling station, either work it there in the refueling station or on the vehicle. That would be a very simple way and a very quick way. As we experimented on the hydrogenation of benzene into a cyclohexane and vice versa. Well, it seems to us it can work quite well, but only the benzene is toxic. As they said, it's not good to be used. So today I say, well, it's very interesting to me to see that you use decalin, and also the decalin then transformed into naphthalene oil. It seems to be quite similar to the reaction of ours, but I have still some doubts, some questions. One is you add also some solvents, as it's mentioned. Which kind of solvent is added? Would that solvent hinders or doesn't interrupt the catalytic reaction of the hydrogen storage alloys we added in or not? That's one. And the second is that naphthalene or decalin harmful to the health and can be used as a organic carrier for the hydrogen or not on the market. Thank you.
In my case of hydrogenation and dehydrogenation catalysis, no solvent are used. Just neat liquid of aromatic compounds, including naphthalene oil, or of course benzene, toluene, and other liquid aromatic compounds can be hydrogenated in neat state. It is necessary to heat up. For example, at 150 degrees Celsius is one example, but the catalysis can act to absorb hydrogen into aromatic organic compounds, and then we can have hydrogenated aromatic compounds such as decalin, cyclohexane, and so on. Now, dehydrogenation in liquid phase is also done without any solvent. I talked on the superheated liquid film state. It's just the neat liquid of decarin or methyl cyclohexane. For catalyst surface, the active site is required to split the carbon-hydrogen bond by giving, in interaction, by giving electron from the side of catalyst active site to the CH sigma star orbital, which is antibonding, and can dissociate that CH bond. So the combination of CH bond and the catalytic active site nature is quite important, so that in some case platinum and platinum rhenium composite or platinum tungsten composite or platinum iridium composite are very effective. But you can notice that these kind of combinations are already tested in petroleum industry. They use that kind of bimetallic catalyst in petroleum refining. You know, the platforming changes into reniforming process, which means that the catalysis, the composite effect between platinum and rhenium, is superior to platinum itself. And I could show that the nickel ruthenium combination was effective as platinum itself. This kind of catalysis is now still underway, so no good theoretical prediction is unestablished yet. So we have to try and try. But I believe that it is very much expectable to have good economical catalyst. Working substances, commodity chemicals, no problem in cost or handling. It's quite easy. And so I guess that kind of approach would show us the way of hydrogen society or hydrogen economy. It might be the same opinion with you.
Alan, would you like to add to that, please?
Well, I think that was well spoken. I think that Professor Saito was referring to is the need to have relatively inexpensive, simple aromatic systems. Environment, health, and safety issues have to be extremely important as far as toxicity, and you mentioned that before with the use of benzene, so that if in the future this was the preferred method of hydrogen delivery and hydrogen storage, that you would have billions of gallons of these liquids being used around the world. And so therefore they'd have to be very safe, and water miscibility, toxicity, things like that would have to be considered, certainly.
Yes. Alan, coming back to the catalysis, you can expect this question from me. Is there any advantage? I see the disadvantages, not the advantages, of having an homogeneous catalyst instead of the palladium supporter thing that you use. In other words, I mean, it's only a fraction of a percent that you need, and something can be. There are so many extremely good organometallic compound that can do the dehydrogenation in a very effective way.
Well, as I mentioned earlier, there are a few homogeneous dehydrogenation catalysts that are known in the literature. They actually, while they have some impressive ability to dehydrogenate molecules such as cyclooctane that normally would be very difficult to dehydrogenate, they have relatively low rates. One advantage you could foresee with a homogeneous catalyst is that could be dissolved into the liquid. And so therefore, as you circulate this liquid throughout the delivery pathway and back to hydrogenation, that the catalyst actually remains embedded with the liquid. And so you could envision that as one way to do this. We've actually been very, very surprised to achieve the high selectivity that we've achieved with homogeneous catalysts. The general rule of thumb is that heterogeneous catalysts can be very non-selective. Homogeneous catalysts can often be much more selective. And so that was a bit of a surprise and a pleasant surprise for us.
Just one comment to that. I don't want to be seen as contradicting my own colleague, and I'm not. But you really don't want to have a catalyst associated with the liquid when it's in the infrastructure, and the reason for that is safety. The liquid alone, no matter what it is, at least the liquids that we've spoken of, will never spontaneously liberate hydrogen, even upon heating. They must have the catalyst. The inability to to give up hydrogen is an enormous safety factor which you do not want to lose. Okay, there's the division of the backyard barbecue, and if you've got the liquid carrier, you throw it on the barbecue, and it will maybe catch fire, maybe smother the barbecue, but you certainly don't want it to boil off hydrogen in the way that you've seen in Alan's video, because that could be quite dangerous. So okay.
Yes, but aren't there scenarios where some of the catalyst is going through a flow-through bed? Some of the catalyst particles are going to ultimately be detached from the bed and left in the residual product, and as time goes and it's recycled many times, the catalyst is going to get in the recycled material.
But you would need, you need not only a few particles. You need if it's homogeneous, it's all there, right? But a few particles, isn't going to make, a few particles in a liquid is not going to make a catalytic dehydrogenation reactor, right? But a homogeneous system would.
And then you'd have to be very sensitive to temperature control then in the event that you had a homogeneous catalyst or a large amount of heterogeneous catalyst that you don't desire to have in the liquid, because then you could get spontaneous hydrogen generation.
Thanks, Professor McDermott.
I don't know whether it's quite appropriate. As a relative newcomer to this fascinating field, to just raise a rhetorical question, and that is that what we have heard during the last few days is some very beautiful inorganic chemistry and very interesting organic chemistry of great potential use in transporting energy in one form or another from one location to another. One of the points that seems to be very important, however, is what energy are we going to try to transport? If we eliminate carbon dioxide producing energy, then it appears from the discussions the main type of energy we are considering transporting is electrical energy. If we eliminate any carbon dioxide producing energy. This then raises, I think, an interesting point of the other alternative sources of energy which we may wish to use. A few minutes ago, comments were raised concerning the presence of boron defect sites. I think here we can learn quite a lot from the whole area of semiconductor physics and the interrelation with chemistry. For example, Honda in Tokyo 25 years or so ago, by using strontium, N-type strontium titanate, had some very interesting results on photo decomposition of water into hydrogen and oxygen. This ran into some problems because of the chemical degradation of the N-type strontium titanate. However, in the view of new types of materials available, this would seem to be a problem which might well be overcome. We have talked about obtaining electrical energy by wind power, tide power, and the like, or solar power. But I think at the same time that we discuss this extremely important question of transporting energy from one place to another in one form or another, we should at the same time bear in mind the alternate ways of producing energy of a technologically useful type, whether it is bioalcohol, whether it is biodiesel, whether it is photoelectrochemical decomposition of water, and the like. So again, since we're talking about hydrogen storage and transportation at this meeting, this is possibly an inappropriate subject to raise. However, I think it is a subject which is in the back of everyone's mind as we run out of energy in the world. If we exclude carbon dioxide producing sources of energy, we need to at the same time be considering sources of energy that we can turn to.
I think that sets a really good context for exactly what we're trying to accomplish. And I think the storage device probably couples to what the energy sources are, and that may have some impacts on what the storage looks like, as well as the storage device needs to couple to the utilization, which is the fuel cell. And I tend to think of a hydrogen storage device and a fuel cell as basically competing with a battery as another example, I think. Any comments from as we seek to close shortly?
Just a comment on that. The hydrogen storage is really driven by the need to store energy in a mobile system, right? That's the point. And it would be less interesting if we really had a way to store that much energy as electricity directly. But some people must have done the calculations. I believe, and hopefully someone can comment, we are far away from that. We are far away from being able to store enough electricity to drive the kind of vehicle that we use at the range of, several hundred miles, right? But since we're closing, and this is Italy, it just made me think of an interesting parallel between what we've just said and, of all people, Guglielmo Marconi. It's kind of interesting. When I think it was the year 1900, something like that, he had done his first experiments on so-called radio at the time, and the Italian government did not want to support him, so he went to England with all his equipment. And when he went through customs, he boasted, and this is interesting, he boasted that he could supplant, with his radio, he could supplant the whole telegraphic structure of the then British Empire. In other words, that that all those wires all over the world that were emanating from London, basically controlling a big chunk of the then modern world, would now be displaced by radio. And the British customs people took so much fright that they actually confiscated all this equipment. But in the end, Marconi was wrong. Radio made it not to replace, an existing infrastructure, but radio rather made it for mobile systems. Okay, the Titanic, the history of this, the Titanic, and all the rest of it. And there's an interesting parallel there. The key is in finding things, for mobile systems. We really have no problem in energy infrastructure with electricity. That's fairly well developed, as was the telegraph at the time, by my analogy. But the problem is in our desire to be mobile, and that's where that's where our challenges lie. And clearly, we don't seem to be able to do with electricity, and we have to do it cleanly. And so, hydrogen is or appears to be the choice, and that's all. That's what we will work for. Thank you.
I used to have a comment from two scientists who has been engaging in lithium borohydride and also lithium boronitride, and materials are classified as onboard materials. From which reason is, of course, thermodynamically speaking, it's a back and forth reaction that you have. But our boron-containing materials, like sodium borohydride, it's classified as an off-board material. So I used to ask you, Andrea, and also Professor Orimo, about your comment on the boron-containing hydrogen storage materials, please.
Sorry, Seichi, I didn't get your question. Can you please say it again?
Okay. Your material, the lithium borohydride, you have been working on the material, and it is so-called onboard materials because of the reversible reactions. So from your point of view, how do you think, and do you have any comment on the off-board boron-containing hydrogen storage materials, I mean?
So you are asking about comparing our direct hydrogen desorption from borohydrides and your process, which is off-board regenerative.
Yes.
Well, I think it would be nice if the borohydrides would allow to have an on-board reversible storage. But I'm not yet convinced that complex hydrides will ever be on-board reversible, because also for alanates we need conditions which would require, or which requires high pressures and rather high temperatures, and therefore it's probably also for alanates better to regenerate them off-board. But I'm really not a specialist for mobile systems, and I mean, we should ask our car manufacturers what they think how a future fueling system for cars should look like. But from the materials point of view, I see both systems are very interesting. The big question for me is for the water reaction with borohydrides, if this is ever going to be reversible between the borax and the borohydride, or if you have to go in the regeneration over the elements, over the complete dissociation of the compound, and in this case it's I think it's energetically not worthwhile to do it, because about 75% of the energy would then be wasted.
Thank you very much.
Can I add just a comment to that? I think onboard reversibility, at least in my personal opinion, onboard reversibility in itself is not the end goal. In the end, it's how much it costs to use a kilogram of hydrogen, for example, in a fuel cell to propel yourself, or to allow you to communicate or to run your laptop for 12 hours without having to plug into a phone. I think, just maybe this is not a entirely politically correct comment, but I think in the end, to bring the fuel cell technology to commercialization, it will come down to the cost factor, the overall system cost.
Can I ask to Professor?
Okay. I'm interested in the, of course, BH system and also NH and also BNH system. All I'm interested in, and all system is so far so stable. That's why I agree with Professor Suda. It's still not on board system, but our research direction is destabilization of the complex hydride, including BNH systems. So that's why in the future I should like to have a destabilized system. In that case, maybe possible to use onboard reversible materials. And also one more comment on BNH system. Just my comment. So I'm pretty sure the most stable phase is ammonia brine compound in the case of BNH system. But if I would add one more element, like for example lithium, we can prepare the completely different compound made from the BNH system. For example, as I explained in my talk, so sometimes we can prepare lithium BH4 and NH2 systems. It's not a stable phase. It's not stable phase, but completely different to the brine ammonia system. Okay, so my challenge is to completely change the atomistic and also electronic structure, even in the metastable phase. But I try to try that. That's my comments.
Thank you very much. Thank you, both of you.
Okay, so this could bring us to a closure of this very interesting morning session. And before we all can cross the courtyard to lunch, Dr. Garibaldi has something.
I have some announcement to do. Lunch is ready. Before lunch, we would like to take a picture of all of us outside the church as a souvenir of this conference and a souvenir of Lucca. Please be back from lunch at 1:30 sharp, because we would like to conclude this conference at 2:45 before the departure of the bus to Pisa. It's a nonsense that one half of the people leave and the other stay here. So please enjoy the lunch, but be here at 1:30 sharp. Thank you.
Okay, why don't we go ahead and start? This is the last lap of the conference, and we aim to end by 2:45, so those that need to be at the airport can leave promptly in the 2:45 bus. So if you can all take your seats, we'd like to start by summarizing the panel discussions that were held after each technical session. Again, the purpose of this conference was really to focus on the technical issues, and then after each facilitator reports out a summary of the panel discussions, we'll have a wrap-up, and Mark Steen from the European Commission will provide a summary reminding people of the overall objectives of IPHE and the next steps, the process, and so forth of forming collaborations and eventually submitting proposals. So the first speaker is Rosario Cantelli, who will summarize the session on metal hydrides.
We were recommended to speak no longer than 5 minutes. Fortunately, we prepared the transparent figures, and I will briefly talk about reversible onboard storage, metal hydride research and development. Però non funziona sta cosa, eh? Okay. So, alanates. Pros and counters. Pros are dehydrating kinetics and cycling behavior. Promising, positive. Counters are capacity less than 5%. The quantitative results obtained up to now are for storage capacity from 3.5 to 5 weight% at temperatures between 100 and 150 degrees centigrade with enthalpies of about 37 kilojoule per mole. The comment is sodium alanates are best and most studied. Other alanates should be explored. Amides. The pros are capacity and cycling behavior. Counters dehydrating kinetics. Quantitative results are promising, from 5 to 9 weight%. Temperatures are still a little bit high, included between 170 and 250 degrees centigrade. Enthalpies 43 kilojoule per mole. Mixed metal amides show promise. Borohydrides. Pros are capacity, counters, kinetics, reversibility in some cases. Quantitative results good, 9% about in weight. Temperature rather high, 300 degrees centigrade. Enthalpies 45 kilojoule per mole. Mixing with binary hydride shows promise. Applications. We have heard about the high-pressure metal hydride tank that has been developed by Toyota. We also heard about optical hydrogenography that has been shown to have diagnostic applications for hydrogen storage. Highlights: adequate dehydrating and rehydrating kinetics have been achieved with sodium alanate. Mixed amides found to have high capacity, reversibility, and improved kinetics. Borohydride binary hydride mixtures found in some cases to be reversible. Mechanism of reversible dehydrating of doped complex hydride found to involve high mobility defect hydrogen complexes. Barrier discussed: reversibility, kinetics, thermal management, and others. Ongoing collaborations, University of Hawaii with the University of Rome La Sapienza, University of Milan, IEFE Norway, General Electric, University of Tohoku. National University of Singapore with Sandia National Laboratory, Institute of Applied Energy, Japan, and Wolf, Germany. Tohoku University with the University of Hawaii, Toyota, University of Fribourg, and Sandia National Laboratory. University of Fribourg with the University of Tohoku, Amsterdam, IFE, University of Birmingham, University of Hiroshima, Toyota, and BMW. Then we have MPI with Opel, General Motors. Those are the ongoing collaborations. Proposed collaborations are University of Rome La Sapienza with the University of Hawaii, University of Milan, and AIST Tsukuba. University of Salford, University of Tohoku, University of Fribourg. That's all. Thank you.
So we'll continue, and then we'll take some questions at the end. So the next speaker is Gavin Walker, who will summarize the high surface area sorbents and carbon-based material session.
Okay then. From the carbon-based materials, high surface area absorbance and novel concepts session, then I'd like to thank Mike Heben and Rishad Shaheen for helping me in the task of reporting on what happened. So with the presentations that we had, then the main scientific and technical results that we feel were coming to the fore there were increased hydrogen storage densities through these metal-assisted systems. Also, it was nice to have the theoretical models as well, helping us to understand what might be happening in the adsorbents, as well as showing the way in which our experimental results and systems might develop. And that there was some theoretical modelling there predicting up to 9% in carbon-based systems, which gives us incentive to continue working in the area to try and realise those types of uptake values. But there's, of course, a need to understand the factors governing the energies of adsorption and how we might design those adsorbents so that we can get enthalpies of adsorption of around about the 6 kilocalorie per mole target that was being shown in many of the presentations. Overall, we had 6 oral presentations, 14 posters. So just to quickly go through the types of systems, there was nanotubes and nanofibers from the carbons, the MOFs, zeolites, inorganic nanotubes, and conducting polymers. I think the interesting thing there is that it's showing quite a wide range of different types of materials, trying to find solutions to the hydrogen storage question. But also, we had a presentation, and there were also some posters included, looking at trying to improve metal hydride kinetics, incorporating things like carbon nanotubes in. And I think an important factor is how are these carbon nanotubes actually affecting the kinetics, in what manner is it affecting the mechanism. There were also included some characterization papers, and I think something that most people in the carbon area will agree with, working on just the carbon side, is that they're not very well characterized. They're not particularly nice materials to characterize. So it's very important, the characterization side. And there's a range of technique-based posters or papers using things like neutron inelastic scattering, proton NMR, and looking at anelastic properties. And as mentioned before, the theoretical papers, they're also very important, helping us to understand the types of interactions that might be occurring with our materials, but also in developing new materials that will hopefully realise significant hydrogen uptakes. And examples there are hydrogen interactions with carbon nanotubes, exploring these Kubas-type complexes, and also looking at carbon-metal hydrogen complexes and how these might be stabilised. So in summarising the collaborations, this list is not going to incorporate all the collaborations for the people that are here at the conference. We went through the posters and the oral papers to try and distill a list of collaborations. So my apologies if there is a collaboration that you've got that's not on here, but I'm sure there'll be opportunities to add to this list, as I assume this information is going to be going up on the web somewhere. So examples include looking at these metal carbon nanotube multi-component systems. It's a collaboration between China and Australia. With the neutron inelastic scattering, then Keith Ross, as he said before, send him your samples. He'd love to do some experiments for you. But there was a particular example in collaboration with CNR in Italy using the ISIS facility in the UK. Also from my own work with the graphitic nanofibers, we're collaborating with Professor Fuji's group at the University of Hiroshima. And again, looking at the characterization of the materials, then dynamic gas adsorption in CNT's project that was between the University of Rome and Max Planck Institute in Germany. And the last one on the list here, metal-assisted CNTs, which is a collaboration that's been going for a number of years now between Richard Shaheen and Mike Heben. So the next couple of slides, we're trying to distill out some of the thoughts that came about from the panel discussion session, and the collaborative areas, potential for new collaborations. We thought it's very important to try and build up collaborations and communications from the theoretical side and the experimental side. So the first two, they might sound rather similar, but it's approaching it from two ends of the story. So combining theoretical models and experimental results for carbon-based systems, but also for other adsorbents. Quite important, looking at the experimental design to try and validate some of these new theoretical predictions. So there's some interesting work going on from the theoretical side. Can we actually produce that in a real system? There was also a feeling that we should try and build up more collaborations across the adsorbents and metal hydride communities, so we could try and collaborate and understand and develop new metal-assisted hydrogen interactions. We're going to, of course, get more innovative ideas if we do look at these cross-multidisciplinary activities. And also, as I said before, characterization of the especially with the carbon systems, is crucial. So looking at new experimental techniques to help understand those materials. So some things that were brought up in the discussion session, then the role of carbon in metal-assisted carbon systems. It's a question that we've got to answer. Is the carbon there just acting as an unreactive support, or is there some synergy between the carbon and the metal? Potential for organic metals was raised as another area of that should be pursued. I don't believe there's been much work in that area yet. With the MOFs, then it'd be nice to see the work not focusing just on the surface area of the materials, but I think there's an awful lot of examples in the literature now, and was presented here as well, where they're trying to modify the chemistry of the MOFs to enhance hydrogen uptake. And an example of that is looking at, is it the oxide tetrahedron where the adsorption is occurring, or is it the organic linkers, and which is going to be the most productive of those two sites to actually target to increase the hydrogen interactions. And last slide, looking at new potential collaborations. This list of collaborations is not an exclusive list, and it's, as you can see from the names of the participants down there, it was really developed by myself and my two co-chairs. So my apologies for the limited range of collaborations in it involving those three institutions, an awful lot. Again, we would like to invite any other groups that would either like to contribute to these themes or have other areas of collaboration to pass on that information to us. So some examples, continuing the single-walled nanotube system designs between NREL and HRI. There are a number of groups that are working on metal-assisted carbon-based materials, but the carbon substrates themselves are very different. So building up some collaborations across those different carbon systems could lead to some real breakthroughs in our understanding. So some groups there would be Nottingham, NREL, Oak Ridge, and a question mark to include any other groups that have interests in those areas. There's a collaboration being proposed by HRI, Max Planck and Caltech, looking at modified carbon-based systems. Also looking at thermal management issues in metal hydride systems, and can us in the carbon community help with that, looking at incorporating nanotubes into the metal hydride particles to improve the thermal management. On the characterization side, analytic spectroscopy from Cantelli, that's going to be a collaboration with NREL, or a proposed collaboration. And also, again, with a number of systems, people are interested in using boron and nitrogen to substitute into the lattice. So building up some communication between the groups working in those areas, especially across the theoretical and experimentalists. And thank you for listening.
Thanks, Kevin. And so now Gary Sandrock will summarize the discussions and activities in the stationary storage session.
Okay, I guess our session sort of covered everything other than vehicular storage. It hydrogen transport, off-board storage, and stationary application of many kinds. In fact, the world of hydride applications, and you can say the same about any other successful medium, is quite elaborate. We've covered only this vehicular area. There are stationary, portable, or thermal compression application, not only the compression of hydrogen, but closed thermodynamic systems. There are separation of isotopes, mixed gas, purification, Gettering applications, batteries, and many of you know and own nickel metal hydride batteries, and a number of other odd applications. Several of these actually were covered, if you look closely, either in the posters or in the talks and places. But we're going to focus mostly on stationary and allude to some of these other stationary, portable, and allude to some of the other applications. In general, the feeling with stationary, I think, contributed mostly by our industrial partner Air Liquide, is that large-scale storage of hydrogen is not likely via metal hydride, simply because the ratio of the high cost of the metal to the relatively to the hydrogen value here. Large-scale storage is going to be underground or underwater systems, or even in bladder-type systems or high-pressure systems. The oral presentations were three, were the smallest session, and I maybe should be the shortest speaker then. All of these three speakers, France, Japan, Russian Federation, talked about what are sometimes called the metallic hydrides or intermetallic hydrides, those things that will work well near room temperature but have relatively low capacity, less than 2%. I've listed the poster presentations that are applicable to this particular topic. There were a few on the low temperature hydrides, these, and I've also listed the poster presentations on magnesium. Whether magnesium is a good stationary or portable storage system was somewhat debated in our session, as you remember here, relative to the problem of the high temperature enthalpy needed for the desorption here, but I'll get back to that in a minute. The status that sort of came out of the meeting is that there are many low-temperature hydrides available, the intermetallic compounds, AB5, AB, AB2, the body-centered cubic solid solution nanocrystalline magnesium and alloys and composites. these alloys, except for magnesium, can easily be fine-tuned thermodynamically, but offer only about 2 weight percent. The general feeling that 2 weight percent will certainly fit in many smaller scale applications depending on the price of that 2 weight percent. Magnesium offers great weight percent, but not so easily tuned thermodynamically. That's the problem we discussed. And there are many secondary non-thermodynamic properties that are unknown and need to be developed. And the exact requirements for these many applications I've talked about are not always known. We're going to need some interaction between those who are building and designing devices and those of us that are making material to fill them. So the important secondary properties that came out of our meeting were these: the cost of the material as sort of a primary consideration in medium to even small size application. That means the raw materials cost and the production cost. There's optimum manufacturing. There's debate on magnesium and nanomagnesium, which many of you are working on. Can you really, if you get fine enough, change the thermodynamics of magnesium? Some said yes, probably. Some said no, probably. Some said no, certainly, I suppose. You may know a couple of those. What seems to be largely missed in many of even the old-fashioned hydride, the safety, pyrophoricity, tank bulging, cyclic life is largely unknown. As Seiji said this morning, that's not only gases impurity problem, but disproportionation problems relative to the stability of the alloy or in a metallic itself. Thermal conductivity and heat management is a major problem. Maybe it's not our problem because it's basically a mechanical engineering problem, but we cannot escape it. And again, there was some debate on are there really thermodynamic advantages other than non-kinetic advantages to nano-sized materials. Ongoing collaborations, I haven't been very specific here, but there are a number of them within the IEA, HIA, as you saw me talk on Monday. There are a number of them, very nice ones, within the EC, High Train, High Story, many others. There are a number of bilateral and regional R&D activities. I was at a NISTOR workshop in Iceland a couple of weeks ago. There are many around, and there are others that I probably don't even know about. As far as the new collaborations, I can't be specific as to the individuals involved in the collaboration, but I'm really just focusing on here the areas that seem to come out of our workshop and the talks themselves, and economic analyses of production techniques, especially for nano-sized powder, some interaction between the storage medium scientists and those who run big metallurgical plants or no metallurgy. System designs and duty cycle analyses. Some things like storage depend on how often the storage is used. 1 week is uneconomic. 5, 10, 20 minutes may be economic. So we need the cost and property requirements and the storage material that the storage material developer must use as targets, and we need to get those from the analysis people and the engineers designing things. And if you look at that slide I showed of the mini application, we need to know how the targets we must shoot for change with these many different non-vehicle applications. I think everybody, privately speaking and in the meeting, realizes that systematic safety studies are probably lacking, probably the most important. Maybe it should be the highest on the list here. And even with these relatively benign metallic hydrides of 5, 10, 20, 30 years ago, there are still unknowns relative to their use from a safety point of view. And again, finally, determination. Really look at this nano-sized area. There were several people who didn't feel nano-sized were going to get us there, and several people who did. Certainly nano-sized has gotten us on kinetics. What else can nano-sized materials give us? Thank you.
Thanks, Gary. And now we'll hear from Bill Toomas, who will talk on behalf of the chemical hydrogen storage session co-chairs.
I think the electronic ink is not dry on this one, so we'll
Well, while we're waiting for that to load, why don't we, let me emphasize again that our objectives for this conference were really to just start the process of initiating collaborations, potential future proposals, joint projects, and really what we wanted to do was provide an overview of the current state of the art, recent technical progress in hydrogen storage. There are many experts here in the field as well as newcomers from around the world, and identify some of the key barriers, areas for potential collaboration, and then just start the networking process. So if we can open it up for one or two comments from the audience on other potential collaborations or potential projects, let's do that now. Scott.
I'd like to propose that just as Richard has told us we need to look at excess absorption and physisorption, it might be nice to try and get some excess collaborations out of this meeting. A lot of the collaborations we've just seen probably would happen at any really top-flight technical meeting where international parties come together. But I'd like to propose that it would be nice if we had collaborations across the areas that are reporting out to us. And the way that I see to do this is to look at the various levers we use to keep hydrogen in a small space, be it pressure, temperature, or chemical bonding. Now, the folks at Toyota very nicely showed us what happens when you try and use two of those. And I would suggest that there's a lot of fertility for two areas to work together in a collaboration that might never have happened except for this meeting if you try and go across those boundaries that have no really good reason to exist other than we like to stay in our discipline. And to give two examples, though I don't mean to say they're the best examples, I think the folks here can probably think of better ones. But if we were to use, for example, the ammonium borohydride that Tom Autry talked about that's unstable at room temperature, and put that in a high-pressure tank, would it be stable? Could you reverse back and forth between the BH4, NH4, and BH3, NH3 with just hydrogen pressure at, say, 300 or 700 bar? If so, you'd have a much better material than what was shown to us already. And because it disproportionates at minus 20 C, it should work very, very nicely. One idea. The other one would be that, again, playing off of Tom Autry's poster this time, they've shown that you can change the properties, the thermodynamic properties of the borazane material in their mesoporous scaffolding, but they've only tried one or two different kinds of compounds. We all know that there's just a host of mesoporous materials and a bunch more that can be created with just a little effort. So could the BH3NH3 be put profitably in some other scaffolding, if you will, some other material like multi-walled carbon nanotubes or zeolites or what have you? Or could something else be put in the sort of scaffolding that PNNL has been using? These are the sorts of things I'm thinking about where you're using two of those levers together at a lower amount to try and establish the same kind of storage. Thanks.
Thanks very much, Scott. I think Scott brings up an excellent point in terms of how we tend to stay in our own areas. So thanks for helping us to think outside the box. I think many of us know that there are conferences that we go to that maybe are just specifically metal hydride or more focused on carbon or chemical. So this time we've seen all of them, and I do also encourage you to think across boundaries. Now let's go to Bill Toomas's presentation.
Okay, and I need to apologize to the speakers from this morning because the time allotted for us to put this together will not do justice to the fine talks that we heard this morning. But, eons of solar energy have been stored through biological and geological processes into a material that we use today, where the energy source is also the energy storage material. And so the challenge of chemical hydrogen storage is to capitalize on that same concept. You can store a lot of energy in covalent bonds, but how do you get that energy in there fast, and how do you get it back out in the form of hydrogen is really the challenge. And with chemical hydrogen storage, just an overview, liquid or solid fuel infrastructures may be possible. We saw some examples of that at the conference. A number of concepts have been demonstrated. One of the appealing things is the material hydrogen storage density of these materials look like they'll do fine for the targets that have been put out. Of course, the entire system and what reactor and everything else is going to be needed has to be included as we move forward. And we've seen examples of exothermic and endothermic reactions, all of which have been catalyzed to generate hydrogen. And this is an area not unlike the other areas where regeneration is key. One could envision onboard concepts, but it certainly seems at the moment that off-board regeneration is likely. Energy efficiency is going to be important, not just what the maximum theoretical efficiency is, but what the actual efficiency is as you start to couple. Recyclability of these materials as they're cycled through the hydrogen on, hydrogen off processes. Some of these processes, based on the thermodynamics, are going to be able to take hydrogen directly and store them. Others are actually going to have other reaction pathways that use energy sources to put hydrogen on, and then H2 would come off. And so we saw three general concepts presented in the posters and the talks at this conference: sodium borohydride hydrolysis, other boron compounds that did not use hydrolysis, and the examples presented were ammonia borane, and some nice talks and posters on dehydrogenation of organics, both carbocyclic systems and also heteroatom substituted systems. And I wanted to point out that there was one poster that looked at ammonia and putting ammonia on coordination complexes as a way of moving ammonia around. So I'd like to go over these three areas and some of the general summary of what we learned from this conference, what some of the key barriers are. For exothermic, sodium borohydride hydrolysis is exothermic. There are catalysts out there that have been looked at. There are systems that are out there. We heard some hydrogen generation systems from Professor Suda, from Ying Wu from Millennium Cell, and there were several examples in the posters. Air Liquide talked about the stability of those solutions, and we also saw a very nice poster from Daimler Chrysler about the Natrium car and some of the positive attributes of that and some of the work that still has to be done to deal with some of the systems engineering and materials compatibility. I don't think I'd surprise anyone in the audience that regeneration is really the linchpin for this system, taking a very stable BO bond and getting it back to a BH bond. It's all about energy efficiency. We saw some economic analyses and some cost estimates, both from Italy and from Air Liquide. It seemed that certainly the main cost element there was the sodium metal. And certainly we saw some talks from Ying Wu at Millennium Cell and Professor Suda about other concepts of trying to reduce the cost of the reducing equivalents, whether it was improved ways to make sodium metal or whether it was actually ways to actually get around sodium metal and get to other reductants. And so, although there are a number of issues that still need to be worked, regeneration efficiency and developing pathways that allow you to at least get closer to the theoretical efficiency for BO to BH. And I would like to point out that if you look at the theoretical efficiency of going back BO to BH, you are within the DOE targets from an energy efficiency standpoint. Of course, right now there is no pathway that exists there. So fundamentally, it's not off the table, but from a pragmatic standpoint, we still need to increase the energy efficiency. Boron nitrogen compounds, the attempt is to avoid the formation of a stable BO bond. I think the most appealing aspect of these materials is the remarkably high amounts of hydrogen that are on these materials. We saw several hydrogen generation concepts in the posters and in the talks. Tom Autry talked about the mechanism of the thermal decomposition for this reaction in his talk, and I think people have seen his poster where they've looked at the effects of scaffolds to reduce the kinetic barriers for dehydrogenation. RTI has some concepts for how to do the thermal decomposition, and some other work, Los Alamos catalyst development, and Mark Bowden's poster talked about some substituent effects on thermodynamics and pathways. This one is where it looks like you can get the hydrogen off, but now the trick is going to be to put the hydrogen back on these spent materials, and so that really is where we are on BNHX regeneration. The last one, we saw a couple of really nice talks from Professor Saito and Alan Cooper on endothermic hydrogen generation from organic systems. Thermodynamics depends on the structure. Air products is very nicely shown. Heteroatom substitution can favorably alter those thermodynamics. There's been a lot of work, but probably a lot more work that needs to happen in catalyst development, both from a rate standpoint and from the ability to use non-precious metals on board a vehicle. So catalyst development is one of the key barriers there. So we didn't catalog all of the collaborations except to note that there were 3 that were in the sessions. Millennium Cell working with Icelandic New Energy, RTI working with the State Scientific Research Center in Moscow, and some discussions that Los Alamos and PNNL have been having with the Industrial Research Laboratory at New Zealand. I would not presume to tell you about any collaborations I don't know about, but I'm sure there are a number of others. Some of the areas that probably make sense for collaboration are, this is really a chemical process. It's about developing catalysts and catalytic processes to make these chemical processes go, whether that's rates, heat management, or the type of catalyst. The impurities and the impurity tolerance that the fuel cell can and will handle, and heat and materials balance with the fuel cell. Pretty interesting infrastructure questions in off-board regeneration in general, and what that might look like, and what some systems analysis might look like for that. One of the really appealing things to chemical hydrogen storage is these are fairly tractable materials. Most of them are molecular or oligomeric. They're very amenable to spectroscopic probes and mechanistic understanding, the way Tom showed us today for the ammonia borane system. And this is an area that theory does a very good job on systems at this size right now, and can be useful for calculating thermodynamics and even for postulating some reaction intermediates. Onboard reactors, there's been some fairly simple concepts advanced, and we probably have some opportunity to develop some other concepts there. And as I said already, overall system engineering and materials compatibility is going to be interesting and important in these reactive systems as well. And off-board regeneration, one of the themes that certainly came through is, if we're not going to just use hydrogen to put hydrogen back on for hydrogen storage, we probably need to come up with some less expensive reducing equivalents as we do our reduction, and build the reduction power back into the system that will then deliver hydrogen. So that was all I had. Thanks.
So now we'll step back, and Mark Steen from the European Commission will give us an overview and reminder of the objectives of IPHE and what the next steps are.
Thank you, Sunita. Okay. The International Partnership for the Hydrogen Economy, under which auspices this conference has been organized, has a mission statement. And I will read it carefully with you on this slide: to serve as a mechanism to organize and implement effective, efficient, and focused international research, development, demonstration, and commercial utilization activities which are related to hydrogen and fuel cell technologies. It's a mouthful, but there are a number of key words in there. It is an organization which has as prime objective to serve as a mechanism to organize and implement. So it has a facilitating function. It is not a money pot. The International Partnership for the Hydrogen Economy has as signatures national member states, no organizations. That's also a point that you should consider. And any additional information you want to retrieve, you can easily find on the website, which is indicated on the bottom left corner. Oops. Now, the International Partnership for the Hydrogen Economy has two superimposed organizational bodies. One is a very high-level steering committee. Representatives from all the IFE members take the strategic decisions on the partnership. There is a second body, which is the working horse of the platform, if you wish, or of the partnership, which has a facilitating function explicitly, and it's called the Implementation and Liaison Committee. And the Implementation and Liaison Committee has been set up now more than 18 months ago, and it has as tasks to provide a forum for information exchange and discussing collaboration between the national representatives to IFE, from where recommendations can be forwarded to policy and decision makers of the IFE member states. This high-level function crystallizes or boils down into a number of more down-to-the-ground objectives, of the Implementation and Liaison Committee, and in fact tasks of which it has been charged, namely to identify scope of research and demonstration activities which can benefit from IFE collaboration or other dimension. And this has already crystallized in the setting up of 5 so-called scoping papers. One related to hydrogen storage, one related to hydrogen production, one related to fuel cells, one related to regulations, codes and standards, and the final one related to socio-economics. Now these 5 scoping papers, who have been discussed and approved at Implementation and Liaison Committee level, who have also been endorsed by the steering committee, in fact set out the big picture, what the representatives from the national members of IPHE considered to be the research priorities. And again, these papers are public and you can consult them on the IPHE website. A second very tangible object or work of the Implementation and Liaison Committee is its function to acting as a catalyst for cooperation and for facilitating harmonization of activities by the members, which are related to topics which had been identified in the scoping papers, and also